Yes. Good evening, everybody. Yeah, started recording now. So, yes, the objective we're going to understand virtually what we have here is what I placed on the timetable to understand and be able to run with SPSS, Pearson chi-square, yet corrected chi-square, likelihood ratio chi-square, Fisher exact P, chi-square for trend, chi-square for test of goodness of fit, McNeman chi-square and McNeman-Bowker chi-square. We also look at relative risk and odds ratio and confidence interval of this relative risk and odds ratio. Historical background about chi-square. No, before I do that, don't let me assume too much. The people that have been following our training, our lecture, we realize that there are some assumptions, behind hypothesis test. So you don't just go and say, I'm going to do tests. The type of test you conduct depends on a lot of things. Like three most important things there. When we say study, I don't want to use the word study design. Are you dealing with two groups, or are you dealing with only one group? A simple cross-sectional study, or you are dealing with many groups? Can be two, can be three. When you are having two groups or three groups, are they independent group or they are peer group? The meaning of independent group is maybe you do something urban rural. You want to know, because I like using what is simple to understand by everybody. You want to know percentage of anemia among children in urban community and in rural community. You have two group of people. But those two groups are independent group because the people in urban, they are different from the people in rural. When you take your measurement in urban and rural, they are different things. The person that is a particular child that is in rural will not be in urban. It has to be in any of them. Even if you have rural, urban, and suburban, they are all independent group. That's the meaning of independent group. And if you now summarize because hemoglobin concentration itself is quantitatively regulated, by the time you have a cutoff less than this is anemia. Anemic, no anemic. So you just divide them to anemic, no anemic. You will be able to know the prevalence of anemia, the proportion, the percentage that have anemia. You are dealing with categorical variable now in the sense that prevalent proportion that have anemia, yes or no, is categorical. And you are dealing with independent group, that is urban and rural. So can you see, that is why chi-square is for association between two categorical variables, because the outcome variable is categorical. Can you see? Anemic, not anemic, is categorical. Rural, urban, anything group is categorical. So that is, chi-square is for association between categorical variables. That is, you are testing the proportion of the outcome between the different categories of the exposure. Now, what I want to say here about independent group is that this example I given is independent group. But let's say you did the same thing, you do this thing for a particular, maybe only one community, or all of them, they are together as one group, and later you are able to know the proportion that is anemic and not anemic, and you now give them some treatment or whatever you did. You went back after 6 months or months to do the same thing for the same group of people, all the people involved. You test the children again to classify them into anemia, not anemia. In this case now, is you have two groups of data also, data set like before, but this one differ because there are two dependent groups. It's from the same group of people. That is what we call peer group or dependent group. Because the measurement you measured before is from the same set of people. If somebody was anemic before, is still anemic, somehow it affects it. So whenever the observation is from the same group of people before and after, what we call before and after, is pair. So the word pair is a misnomer in the sense that people, when you say pair, people now think maybe you are pairing group of people, two group of people. No, you are not pairing. What actually you are pairing is not the subject. What you are pairing now is the observation, the group of data you collected. So independent group means that this group of data, two group of data are from two group of subjects. That's independent group. But the pair group, which is dependent group, this group of data are from the same group of people. I think it's very clear now. So that is one. So whether you are dealing with one group, or maybe many group, or two group, or three, or even those two groups are they before and after, it has effects on the type of that analysis you do. Why I don't want to use the word study design is that when study design is broader, because it's not everything about study design that affect analysis. Experimental design, it has nothing to do with analysis apart from the fact that experimental design usually have comparison group, and there are observational study also that have comparison group. So what computer does not know if someone you did experiment or not. What computer knows is, are you dealing with one group or two group or three group? These two groups, are they before and after? That is what the computer will know. So that is why I just use the word simple. The group you are dealing with is a factor. The other factor is the type of variable you are dealing with. Are you dealing with categorical or quantitative variable? So we already know that chi-square is for categorical variable. Then the third one is that whether this test follow the variable you are measuring, does it follow a pattern, a theoretical distribution? Let's just say, does it follow normal distribution? So if those one, you need something to follow a variable, the data set to follow normal distribution, we call it parametric test. Why the one you don't actually need is non-parametric. Like chi-square now is one of the non-parametric in the sense that after all, our chi-square is for categorical variables. So even those variables, they don't follow normal distribution. So I think that's a background, because I just gave that background because of people that are new to my lecture, because we have given, from the beginning, we've talked about basic concepts of statistics, descriptive statistics, differential statistics, probability and normal distribution, assumption around hypothesis testing, before we came down to this. Now, this chi-square that is so popular, that people know less about it, don't know much about it, historical background. It was first described by a man called Capelson. He lived in London from 1857 to 1936. He was considered to be the founder of mathematical statistics. He developed the chi-square test. He published it in July 1900. He coined the term standard deviation. That standard deviation here is was the one that coined it. And he developed the product moment correlation. That's the one they call Pearson correlation. So he was the first to describe correlation. So before some other people now describe the one they can use for non-parametric, anything that do not follow normal distribution, all those Spearman and Kendall, while described after Pearson described the Pearson correlation, which is called product moment correlation. So I've introduced Pearson to you. Now let's look at, before you can understand the origin of chi-square, I just want us to have an overview of what you already know. If you already know, you've heard of normal distribution. I want to quickly look at just a short overview of standard normal distribution, because that is the origin. That was the origin of chi-square. Now, we know that those variables that follow normal distribution, like most biological variable and social science variable, like all those weight, height, whatever, blood sugar, blood pressure, then IQ, and some other social science variable that follow normal distribution. If you plot, we already know that if you plot it, when the shape you are seeing normally distributed, it goes up and come down. It is bilaterally symmetrical. It's like a bell shape. Why it goes up, the logic behind it is that as the value of that variable, maybe you start from the lowest that people may have, as the value increases, the number of people that have it increases. That what you have as the vertical is the frequency, the horizontal is the value. So as the value increases, maybe height, weight now, as the value maybe 40 to 45, 45 now, the adults that will weigh 45 will be more than 40. The adults that weigh 50 will be more than those that weigh 45. The adult that weigh 55 will be more than weigh 50. The adult that weigh 60 will be more, up to maybe 65, up to 70. But when that is why the frequency is increasing. Can you see now? That's why it's going up. Because the number that have the value and the value goes up, the number goes up. It then reaches a level, let's say for weight now, maybe it reaches 70. Anything that goes beyond 70, the adult that weighs more than 70 will be less than the one that weighs 70. As you are going to 80, the adult that weight that value become less as you go to 100. That is why the graph is like that. And the way it is bilaterally symmetrical. But if you plot this graph for all those variables that follow normal distribution, you know what you have. You will have the same shape, but you have different graph that will different scale, because the scale of measurement differ. Like for example, kilometer. So remember when you were doing physics in secondary school, when they say you tell us the scale on the graph sheet, 1 kilometer represent 1 centimeter represent 10 kilometer. You have to let us know. So if you have to plot for this graph for many things, you have to give us different scale. So each of them have their own, even though there are something that are common to them, the shape, they have their own. So the intelligent people now come up with, instead of having, let's have standard normal distribution, which is what I have here. What I have here is not normal, it's a standard normal distribution. Instead of now talking of the number, the value, we are talking of the number of standard deviation each observation. Okay, look at example now. So I'm just giving an example, it's not part of it, just because if you don't understand, because the chi-square is from standard normal deviation. Now, the example I gave that time when I was presenting was that, let's say an adult, a group of adults that go for, women that go for training to reduce weight, exercise program, and you now bring some of them. If the mean of their weight in the population is 70, I give an example, I put this example. This is the mu. The mean in the population is represented by mu. That is the this Greek letter. The standard deviation in the population is represented by rho. Is Greek letter also. This x is used to represent the value of each person, maybe your weight. So if let's say the mean, for example, is 17 and the standard deviation is 10 in the population, if somebody that weighs 60, weigh 80 come, if you remove, look at it, you remove the mean from the value, the score of that person, the mean is 17. If you remove the mean 70 from 80, it give you 10. And if the standard deviation is 10, 10 divided by 10, it give you 1. If the person that weigh 90 come, you remove 70 from 90, it give you 2, a 20. You divide 20 by 10, it give you 2. If it is person that weighs 60, you remove 70 from 60, it give you minus 10. When you divide by 10, it give you minus 1. If the person that weighs 50, you come, you remove 70 from it, it give you minus 20. You divide minus 20 by 10, it give you minus 2. Can you see now? The issue, the person that weighs 90 is 20 kilogram more, but it's 2 standard deviation because it's 2 more than the standard, 2 times more than the standard deviation. It's plus 2 standard deviation. The person that weighs 50 is minus 20. When you remove 70 from it, it's minus 20 lower. When you divide minus 20 by 10, it gives you minus 2. So you can represent each people's weight by the number of standard deviation you weigh. The people one that carry positive means that they are above the mean. There's 2 standard deviation above the mean, 1 standard deviation above the mean. The one that are negative mean they are below the mean. 1 standard deviation below the mean, 2 standard deviation below. So you can represent people's value instead of representing by the weight. If it is meter by meter, instead of if it is distance by kilometer, you now represent it by the number of standard deviation away from the mean. That number of standard deviation away from it is called Z-score. z-score. And if you now plot normal distribution based on z-score, it's standard because it's a ratio. What is a ratio? A ratio is something that when you divide two variables of the same unit, the unit will cancel out. It has no unit. Z-score is a ratio. You cannot say 2 kilogram. No. 2 meter. No. Z-score is a ratio. Okay, if you say 400 kilometers over 4 hours, it will give you 400 kilometers per hour because the numerator is measured in kilometer, the denominator in hour. But if you divide 400 kilometers by 100 kilometers, it gives you 4. It's a ratio. It gives you 4 because kilometer cancel kilometer. That's what we are saying. If you divide weight by weight, if you look at this thing, the mean you are removing is in kilo, is in the same unit, maybe in kilogram. The standard deviation is in kilogram. If you do it, you are kilogram cancel kilogram. That is why it's a ratio. So if you now plot, it gives you a standard normal distribution that the mean is 0. You know why the mean is 0? Because the people that are 0, they are the ones that are coincide with the mean. When you remove mean from there, it gives you 0. That's why the mean is 0. And the area under the graph is 1. Every probability density function. Anyway, probability, I wish anybody that come for my training has received those training where I broke down the meaning of all those probability function, probability and normal distribution, all those this thing. We won't be having a day explaining some of those things. So anything, any probability distribution is the total area is 1 because probability cannot be more than 1. So this one, the total area is 1. And the mean is 0 and the standard deviation is 1. You know what? The standard deviation, anybody that's 1 standard deviation, that has a value that is 1 standard deviation. When you now divide by that, it gives you 1. That's why the standard deviation is 1. Then the mean is 0, the area is 1. So for you to even prove further, to prove that the area is 1, you know that if 1 and 100 is the same, 1 and 100, because 20 and 0.2 is the same, 20% and 0.2 is the same. So 100% and 1 is the same. It's just a matter of multiplying by 100 or dividing by 100. Now, how do you prove that this area is on a 1? We know that in normal distribution is bilaterally symmetrical. Both sides are, one side is a mirror image of the other one. If that is the case, so half, this one is half, this one is half, half plus half is 1. That's one way, crude way of proving it. So this is standard normal distribution, is universal. It's used in any field, in engineering, in medicine, in anything. It's the same. Because you have converted the measurement, that particular thing, to the z-score. So once you convert it, it has no unit. Now, some are negative, some are positive. That is z-score for you. Now, I will not dwell much about that because we are not actually here for that. Now, I want to explain how chi-square originated from this. So I want to entertain question concerning this one. I just say, any question? Quickly, let me trash it out before we move ahead. Any question? Any question?
Thank you, sir.
Yes, that's great.
Thank you, sir. Yes. I was trying to find out. I wanted to understand the part where you were explaining about the under the curve, 100%.
Under what?
You mentioned that the area under the curve is 100%.
Hold on, doctor. Dr. Khaldi, mute yourself. He's making noise. Dr. K. Okay, go on, Dr. Ugo. Go on.
Okay, you mentioned that the area under the curve is 100%. I missed that part where you were talking about because the probability. The probability is cannot be, of course, more than 1. You said that the area under the curve is 1.
Yes. Yes, that is the area. What they just mean, just very simple. This my phone as I'm holding it is 1. That is 1. It's a whole number 1. If I divide into 2 equal half, become half. That's what it just means.
Yeah.
So it's considered that the whole probability is 1 as a whole number as 1. And the 1 you can convert 1 means 100%. Yes, I'm now. If they say something,
yes,
you have a yam now, or bread. Somebody take 50%
yes,
of that, you take half of it. If somebody take
half of
40%,
it, yes,
it means 40% means 0.4. Converting between 100
yes.
and 1 is
Okay,
dividing by 100 or multiplied by 100. That's what I said. And
okay,
I just
okay.
explained, if they say something is, and that is bilaterally symmetrical. One half is the mirror image of the other. So the other half
Yes.
is half, the other one is half. So the whole is 1. Do you get the
Okay.
picture now? It's just
Okay, I
like you have a
understand.
piece of something that
Yes,
is from it, people can detach from. The whole of it is 1. So I think we'll proceed.
okay.
There's more much I can say about, because I try to teach people from first principle. But sometimes if there's a foundation you need before you move. All this one I've said better. I'm trying to, because there's some people like Wovina and Afefi, they have not been following our this thing,
Okay.
our session. So, and I don't want them to be late. That's why I even try to go to that extent. So to explain, I know that you want to know all things, because you have.
Yes.
It's
No.
good. It's good. It's
Because
good. So any other
thank you,
question
sir.
before we
Okay.
proceed? Any other question? Don't worry, we'll move forward. We'll cover everything. Any other question before we proceed? Okay,
Hello, sir. Hello,
okay.
sir.
Go on, sir.
Yes, sir. I don't know if you can just briefly share more light. At a point, it was very clear how standardization becomes 1. You were explaining some things, but at least this one you just explained was a bit clear. But the standardization, from the graph you showed us the Gaussian distributions.
Okay.
The winding was the 0, standardization was 1.
Okay. I will
And
explain.
I was seeing have different. You said we divide something by, so it become a bit not 100% settled.
Okay. Look at it again. What
Yes,
I
sir.
just say is not even the graph now. If you look at this x minus mu, so the mu is the
Yes, sir.
mean in the population. The mean in the population.
Yes, sir.
The row, the one down, is the standard deviation in the population, right? So I just give.
Okay. Yes, sir. Yes, sir.
Whenever you give this, I gave an hypothetical example, but it's applicable to everything. But for you to be able to conceptualize, I give that hypothetical example. That okay, maybe
Okay,
if
sir.
other people are having the same problem, I want to quickly, within 1 minute, share with you the slides for when I was treating that part. I think should be under probability and normal distribution. So that slide, I put a picture of some women. Please, if it's you, Dr. Carl, just mute yourself, because you like and something's making noise in your place there. So thank you for doing that. So this is what I want to. Okay, let me come and share. I'm gonna come and share with you before. I just assume that. Let me share I've opened it now. Which one? Wait to. All right. Probability. Okay. You can you all see? Okay. Why is he? Just wait. Why is he? Okay. No problem. Can you see what I share now?
Yes, sir.
You can see a group of women. Hello?
Yes, sir.
Yes, look at this group of women.
Yes, sir.
Yes. This is what I used to explain that time. This group of women, they are part of just an hypothetical example. They are part of a weight reduction program. So in the among the maybe up to 1,000 of people enrolled, there are plenty. It was found that the mean weight among them was 70 kg, and the standard deviation was 10 kg. It's just an example. If some of them now post, 5 of them post for picture because they wore uniform and post for picture, you know that if the mean, and you want to know how far away each of them is from the mean. You want to know the difference between each value and the mean, right? How deviated each of them from the mean. This person that is 70 kg, you know the mean is 70 kg, and this mean is the mu. The x is individual value, and the standard deviation is the one below now. You are dividing. So when you want to minus mean from the x, this person is at 70, and the mean is 70. She happened to weigh 70. When you remove 70 to 70, it will be 0. So our own deviation from the mean will be 0. This person that is 80, our own deviation from the mean, if you remove mean from 80, it will be 20, right? Then when you divide 20 by 10, which is, it will be 10 rather. 70 minus 80 is 10. When you divide 10 by 10, which is the standard deviation, it will give you 1. Whereas the person that weigh 70, when you remove 70 from 70 is 0. 0 divided by 10, it still gives you 0. So the person that weigh 90, you remove 70 from 90, it gives you 20. 20 divided by 10, which is the standard deviation, it gives you 2. The person that weighs 60, when you remove 70 from 60, it will be minus 10, right? 7, because you are removing, you say 60 minus 70 is minus 10. Divided by 10, it gives you minus 1. And the person that weighs 50, 50 minus 70, it will be minus 20. Divided by 10, it will be minus 2. Can you see now? Each of them, what you do is to look at their deviation from the mean. Those ones that are higher than the mean, their own deviation will be positive because you actually remove mean from each of them to calculate the deviation. The ones that are lower than the mean, the deviation will be negative. When you now divide that deviation by x minus x by my mu is the deviation. When you now divide the deviation by the number of standard deviation, it will give you the number of standard deviation. What you are saying, how many standard deviation in that deviation? I don't know, how many standard deviation can we see in the deviation from the mean? So the person that weighs 90 has 20 as a difference, divided by 10, it gives you 2. So that person is 2 standard deviation above the mean. That is why it's positive. The person that weighs 80 is 1 standard deviation above the mean. The person that weighs 70 don't deviate from the mean, is 0. And the person that weighs 60 is 1 standard deviation below the mean. And the person that weighs 50 is 2 standard deviation below the mean. Why the mean is 0? Now, we now say that instead of you talking about their weight, we are talking about how many standard deviation away from the mean. That number of standard deviation away from the mean is called z-score, is Z. And that is what we are looking at. And we know that when you now plot that standard normal deviation in standard normal plot is the plot of that particular z-score. So when you now use z-score instead of the real value, you now use z-score to follow normal distribution. It's perfect. So it's universal in the sense that you can change anything to z-score by just calculating the deviation divided by the standard deviation for that particular thing. You calculate the deviation of each value from the mean, and that divide by the standard deviation to give you the number of standard deviation away from the mean each observation is, and now plot it. You see now? So because why the mean is 0, the question you have is because the mean, the person that have the value that correspond with the mean, when you remove it from the mean from mean, it will give you 0 divided by the standard deviation. So when you are considering the number of standard deviation away from the mean, that person did not deviate from the mean. That's why the number of standard deviation away from the mean is 0. And the mean is the one in the middle. That is why in the standard normal distribution, the mean, what is just telling you the mean is 0, that is where the mean of the value that correspond with the mean in the population also. So the mean is 0. And any other thing is above the mean or below the mean. I don't know if that one has answered your question a bit, Dr. Kayode.
Yes, sir.
Okay, that's great. Any other one? Welcome. Any other one? Okay, we'll proceed. No other question? Okay. Let's proceed. Now, you will see that for this standard normal deviate, the standard normal distribution, what you use to plot it is z-score or the standard normal deviate. It's the same thing. What they call standard normal deviate is the z-score. It's another name for it. That's what you use to plot it. You can see some value are minus 3, minus 2. Though we just show whole number here. It can be minus 3.2, can be minus 2 point something. So if you remember, the standard normal deviate that corresponds with 95% level of significance is 1.96. So I will not waste time explaining that, because it's actually, that's not for, it's not subject for discussion now. It's something that you are supposed to have, okay, we have talked about before this time. So it can be named, they just show only the whole number here. Now, where I'm going to now is, here. The square, chi-square is the square of that standard normal deviate. The standard normal deviate follow normal distribution. I can see it. Some have negative, some are positive. But if you square, that was what Pearson did. That was the origin of chi-square, how they discovered chi-square. So if you square the standard normal deviate, of course, all those ones that are negative, they won't be negative because if you square negative, it will become positive. Minus 3 times minus 3 will be plus 9. So that is why the distribution is no more bilaterally symmetrical. The chi-square distribution is now skewed to the right. Now, no more negative. It's from 0 to infinity. It makes sense. You will see that the chi-square at the initial, it first of all peak on this side and now begin to flatten towards the right side as the value increases. You know that if you look at the graph where it originates from, the value that are close to 0, the smaller value, they have highest frequency. That's why around the 0 is the peak. So the value that are smaller have the highest frequency. As the value are increasing both on the negative or positive side, the frequency becomes smaller. So when you square it now, all the negative and the positive, they are on the same side. There's no more negative. But you know that because the frequency of the one that have smaller value, they are more. So it's the same thing. That is why when you square it now, all of them come to one side, no more negative from 0 to infinity. But you're going to see that the majority will be at the earlier part of the graph. So as the value increases along the horizontal, the frequency decreases. That's why it's flattening. That's why it's skewed. No negative value mean is equal to the degree of freedom. We'll talk about degree of freedom later. Now, even though it was discovered through this process, it was discovered later that many things, statistics follow this pattern. So God is so wonderful. This chi-square and some other distribution, even t-test and all those F-test you go to discover, all of them, they are somehow related to the normal distribution. It's only the normal distribution that come out to us that we're able to recognize that underneath all this one, if you do something to that normal distribution, it will give you those hidden ones, especially this chi-square. So a lot of things follow this chi-square. So what do you want to know? The properties of this chi-square. It is not symmetrical like normal distribution. That's the first thing. It ranges from 0 to infinity, no negative value. You know the reason for that now. Skew to the right. You know the reason is skew to the right. I've explained it there. Total area under the curve is 1. Any probability distribution, there is no actually any distribution that the total area is not 1, because probability distribution, the probability cannot be more than 1. So just like normal distribution, any other distribution, the total area is 1. The family is a family of distribution. You're going to see later. The shape vary based on the degree of freedom. So we'll talk about that. That's the next thing we want to talk about. The last two, the test utilizes a contingency table, and these two, don't worry, I will not tell you now. The next slide, when we explain, it will be clear. Number 6 and 7, we explain. Let's look at the issue of contingency statement, because this chi-square is used to look for association or find or test association between categorical variables, two categorical variables. So when they say something is categorical, it has limited category. That's what it means, like sex, male, female, socioeconomic status, upper, middle, lower. Even if you say ethnicity, it's categorical. Even though in Nigeria we may have up to 300, but we now have a way of, even if that is categorical, but we have a way of collapsing it. When you are collecting your data, you talk about the major one, outside Igbo, Yoruba, and now the rest, you now say others. Unless if you are doing the work where maybe those others are predominant, you now have those, some others are, oh, Kanuri, then others. Whichever way, either you are dealing with 5 or 4 categories, 6 categories, is categorical because they are limited category, unlike continuous variable where you have unlimited number of values. So when you are dealing with 2 categorical, the best way to know the association is to cross-tabulate. So contingency table is also known as cross-tabulation or cross-tab or two-way table, in which you allow one to be along the horizontal, another the categories of one will be arranged along the horizontal, the category of the second one along the vertical. And by convention, it makes more sense to allow the horizontal one to be your exposure variable. So assume that you know the difference between exposure and outcome. Although when we're talking of the initial training on basic concepts, we only talk about quantitative and qualitative variable. I left this one to this time like this. Now, when you are dealing, you are looking at association between 2 variables. One must lead to the other. The one that makes sense that it leads to the other is the exposure or the independent variable. The one that something leads to is the outcome or the dependent variable. For example, now, when you're looking at sex and exposure and employment status, employment status cannot determine somebody's sex, but somebody's sex can determine the employment status. That is, somebody may be employed or unemployed because it's a male or female. But you cannot say, oh, this person is a male or a female because he's employed or not. Can you see now? But a particular variable that is an outcome variable now, in relationship with another one, it may be an exposure. Look at an example now. We may talk about male and education, sex and education. Education will be outcome because your sex may determine your level of education. Your level of education cannot determine your sex. But when you are not looking at level of education and socioeconomic status, your level of education will reduce the follow. Your level of education will determine your socioeconomic status, not the other way around. Can you see now? So whenever you want to look at 2 variables, you look at them together, you have to determine with your own sense which one should be exposure, which one should be the outcome. And the word exposure and outcome is the same thing as independent and dependent. It's only that in the past, the people that got involved in experimental design, experimental study, they use the word dependent and independent because they do something to influence the variable they want to measure. And that particular thing they do, the group that separate those things is the independent. Whereas that thing they are measuring is the dependent because it depends. For example, now, if you give education or you give drug to people to measure the blood sugar or blood pressure is the outcome because it depends on the drug. And the what define the drug is the group. Some you give drug, some you didn't give drug. So you have a group you give placebo, you have a group you give the active drug. So that group is the which define placebo or the experimental group or placebo group is your independent variable. While the blood sugar or blood pressure you are measuring is the dependent variable. So they are the one that brought the name. the experimental, but in the among people that do observational or non-experimental research, they look at what is the exposure variable, what is the outcome. There is the same thing. So exposure is like independent variable. The outcome is like dependent variable. And the word exposure, the exposure have many names. Factors, you can call it factor. You can call it determinant. You can call it determinant. You can call it factor. There are many things they even call it. If you remember, many names they call it. They just know. So by convention, when you are doing your table, it makes sense to make your exposure to be along the horizontal and your outcome along the vertical. So what will happen is that it will produce a number of cells. Contingency table will produce a number of cells depending on the category of the outcome and the category of the exposure. That is the category of the.
Sorry, sir. Okay. Excuse me, sir.
Yes, sir.
The exposure should be on the vertical. Is that what you mean?
The exposure should be along the horizontal, like sex now, male is along. Can you say along the horizontal? The exposure should be along the horizontal. The outcome should be vertical.
Okay.
However, it's not a stringent rule, because you may decide, or you may see work that is done otherwise. There are reasons for that. But if care is not taken, the person may misinterpret. When we run the result, we see the interpretation, you will see what I'm saying. It's safer. But if you know the right thing you have been doing it, even if you want to do the other, you know why you are doing it, and you know how to put your percentage properly. There are many people that present results, they misinterpret. I will show you later. But by convention, this is how it's supposed to be. So now you will see that this one, because we have the first example you see here now, the exposure, which is the sex, there are two possible categories, male or female. And the outcome, there are two, which is employment status, there are two possible categories, employee, non-employee, or yes or no. You can see that because both of them are 2 times 2, 4. You have cell, 4 cells. That is the simplest you can have, 2 by 2 table. Because if you cannot say a variable, a categorical variable has only one category, no, it's no more a variable. If you are studying only women, maybe you went to antenatal, which is only women, sex is not a variable, it's a constant, because it does not vary among them. So for something to be a variable, there must be at least 2 possible values. If it's only one possible value, it's not a variable. So there are 2 possible values. So the smallest contingency table you can have is to have exposure variable with 2 possible values and an outcome variable with 2 possible values, making 2 by 2, making 4 cells. Now, this example, the second example, you can see now the level of education, there are 4 possible values: non-formal, primary, secondary, tertiary. So the outcome is there are 3 possible values: upper, middle, lower. So when you multiply, it gives you 12 cells. Does it make sense? So that is contingency table. We'll talk more about that. Now, I think it will lead us. Let's now go further. Is there any other question about that contingency table? If there's no question, we'll move further. Because I want you to be, I don't want you to, because if you don't understand something, the next one, you may not understand. Somebody want to ask a question?
Yes, sir. So it means the exposure is the independent variable. Is that what you said?
Yes.
Okay.
The exposure is the independent variable. The outcome is the dependent, because the dependent variable depend on the independent. The other one, the exposure does not depend on the outcome. That's why it is independent. It's the outcome that depends on the exposure.
Okay.
Okay, that's great. Any other one? To proceed? Okay. Now, there are many test statistics that follow chi-square distribution, as I told you. The one that is often used, the most frequently used, is the Pearson chi-square, named after the person that first described chi-square. Now, what does he actually do? Because it serves the basis for understanding many things, chi-square. That's what I want to quickly explain. What it does is to put the variable in contingency table, as I've just shown us, and now compare what you are seeing on the table which is called observed value, what I've seen on the table. When you do your work, you cross-tabulate what you have seen on the table is the observed pattern or observed value. But it's comparing you with a pattern which you expect. The pattern you expect, because you know the test you are doing is a test of hypothesis. And the hypothesis you are testing is the null hypothesis. You know, when you write your hypothesis, you write it in two sentences, two mutually exclusive sentences, non-hypothesis and alternative hypothesis. Non-hypothesis says there is no association between these two variables, or there's no difference in the outcome between different categories of the exposure. Then the alternative hypothesis says there is an association between those two variables, or there is a difference in the outcome variable between the different categories of the exposure. But you don't test the alternative hypothesis, you test the null hypothesis because that is the only one that is one. Because if you say there's a different, there are infinite number of ways things can be different, and you have to do infinite number of tests. For example, if you say my age differ from your age, it can be differ by 1 day, 2 days, 3 days, 1 week, 1 day, 3 weeks, 1 year, 5 years, infinite number of ways my age can differ from your own. So you are bound to test all of them if you need it, and you will not end the test. But if you say my age and your age is the same, it means the same. So that is why non-hypothesis is the one that is being tested. Of course, both of them are mutually exclusive. Because if the non-hypothesis is true, alternative hypothesis will be false. If the non-hypothesis is false, the alternative hypothesis will be true. The reason for testing non-hypothesis. So the expected value is what you expect in those cells if non-hypothesis is true, that there's no difference. I will explain that one further because sometimes it can be tricky, but I will explain further when we get down. But I just wanted to quickly look at this. A lot of things. The different type of, it's just, let's quickly now, this one just to talk about the different type of tests, chi-square. And it's not all of them we are going to do in our training because it's not all of them that are concerned what we want to do. But the one that are concerned, we'll do. Chi-square, Pearson chi-square, that's what the commonest, that's serve the basis for even our training. Comparison of proportion between independent groups. Just like the type of table we just put now. In the two tables we just put above now, what it's just doing is comparing the proportion that are employed or not employed between male and female. Male and female, there are two different groups. This one is comparing the people that are upper socioeconomic class or middle social or lower socioeconomic class among no formal, primary, secondary, tertiary. These four groups. So when we are talking group, independent group, they are different groups. The person that is under primary is different from the person under secondary and tertiary. Just like male and female different from one another. So the outcome is what you are comparing between the different group of the exposure. So that is what Pearson does. Can you see that the group, the outcome, the group as defined by the outcome now, can be 2 groups, can be 3, can be 4, can be many. The likelihood ratio chi-square is doing the same thing. Both of them also compare between the proportion between independent groups, or saying that they are looking at association between categorical variables. You know, the reason is that if you look at the example we gave now, the employment status is categorical variable. The group, male, female, is categorical variable also. Anything group is categorical. That is why chi-square is about association between two categorical variables. You also test for goodness of fit. I will explain that one. I think I will explain. Don't let me float. I will explain that one later. So both of them, they are actually doing the same thing. Likelihood ratio and Pearson. You're going to see when we run them together. It's their formula that just differ, and the value differs small. But Pearson chi-square. So likelihood ratio, what they just do is to look for alternative way of calculating this chi-square. You will see the logic behind it as we go. McNeman, what it does is that, I explained before and after pair group. If it's the same group of people, it's not independent group. It's not, you cannot use this Pearson, you use McNeman. And also the extension of McNeman, which is McNeman Bowker. We talk about it. We also talk about chi-square for trend. For example, if let's say this outcome variable now is employment, which is yes or no, which is 2 category, and this exposure you see, there are different level of exposure, more than 1, 2, 3, 4, but they are in order. They are ordinal variable in the sense that they look at it. Primary is higher than no formal. Secondary is higher than primary. Tertiary is higher. So it's not just ordinary categorical variable, it's ordinal variable. Those are part of it. It's not nominal. This one is nominal. If it is even employment, if it is ethnicity or marital status that we have 1 to 4 or 5 group here, it's nominal because there's no grading. But this one, educational status, there's grading. It's ordinal variable. So you want to know, okay, how many people that are employed? We have example like that we will run. How many people that are employed among the formal, no formal education and primary? Is it like people that are employed in primary are more, secondary are even more, tertiary are even more? Is there any linear variation? Is there any trend? That is chi-square for trend. So after you calculate PSC, you can calculate chi-square for trend. SPSS give you all these things. Then you now come to all this other one we are not going to do. Chi-square for maintenance chi-square is for stratified analysis. When if we talk, maybe when we talk about removing confounder, we talk about stratified analysis, that's what they use it for. So I will not, because so that we can save time, just know that one. I will not be talking much about that. What statistic is chi-square? What statistic is what we use in some software they use for logistic regression? Is chi-square. Though for SPSS now, it use what statistic? I don't know, maybe Stata use Z, because I know that people use Z. You know, this one is a high opener. If you remember, the origin of chi-square is from Z-score. Normal distribution is square of normal distribution. Somebody was asking me one time when I did analysis, oh, is it that when you run a P4, it gives you Z? Why this one give you chi-square? I said that when you do your logistic regression, the beta, which is the coefficient, the regression coefficient beta, you divide it, if they divide it by the standard error, it gives you is follow normal distribution. That is the same. If you square it, it follow chi-square distribution. That is what statistic? It's like a water and ice block. You need somebody, they give you ice block. Some people they give them water. It's still the same thing. Because if you actually need water, you go and melt the ice block. Or if they give you water, the ice block, you go and freeze it. So when you so some software stop at Z, beta over the standard error. It follows normal distribution. But if you square it, it follows chi-square distribution. That is what SPSS does. While some software they stop at that normal distribution, they just use it like that. It's still the same. So Kuka-Wallis statistic. Kuka-Wallis statistic, you're going to see. Okay, I think we discussed that under assumption for using for hypothesis testing, where we talk about instead of you doing ANOVA, if that is not normally distributed, the data set, no, ANOVA is for comparing more than 2 mean, 3, 4 or more. So if it's not, you follow normal distribution, you do ANOVA. If it doesn't, you do Kuka-Wallis. So Kuka-Wallis test is the non-parametric counterpart of ANOVA, one-way ANOVA. So that Kuka-Wallis is a chi-square. It follows chi-square distribution. Chi-square for heterogeneity used in meta-analysis is chi-square. This is just, there's still many things that follow chi, just for us to academic purpose. Now, requirement for doing this chi-square, especially this Pearson chi-square, if you have been following, the variable must be categorical. That is why chi-square is for association between categorical variable. The two variables you are dealing with must be categorical. That is one thing. If you want to look at association, if the two variables are not categorical, the only thing you can do is to categorize it, like age now. Age is a numerical variable. But age, you can range it to less than 20 to this. When you range it, it becomes categorical and become ordinal. Because when anything that is numerical, you divide into many groups, more than 2 groups, it becomes ordinal. If it is just 2 groups, it's nominal. Like what we do in we want to do diabetic, you measure blood sugar. The underlying factor is the blood sugar, but once the blood sugar is 126 and above, you say diabetic. So those ones that are 126 and above, diabetic, yes. The other one, no. You have categorized it. That group, diabetic, yes, no, is no more. It's not a category. It's not a quantitative. It's a categorical variable. It's the blood sugar that is quantitative. That is continuous variable. But the category, the diabetic or not, or hypertensive or not, you're categorical. Or your age group, you're categorical. So when you are dealing, for you to do chi-square, the 2 variables must be categorical. 2 or more categories, I've explained that. You cannot say one has 1 category, only female. You know, they say some people they try and go and put table because only female, there's no male there. How can you say they are calculating chi-square? How will you do that? Independent of observation. But however, this one can be violated. This one only true for Pearson chi-square. For McNeman, it doesn't really have to. Independent means that you are measuring the outcome variable in between 2 or 3 or more than, that is independent group, as I said, like urban rural. That was it telling you. That's for independent for Pearson. But for McNeman, it may be the same group of people. Let's take very large sample size. This one is very, very important. I will go to explain it further later. I will skip this, but just know that it must have large sample size. I will explain the reason later. That is the reason you see that chi-square is not valid, because if your samples are very small and your contingency weighting will have many cells, you're going to see some cell with expected value less than 10. I will come back there. I will explain it. Now, I've explained that. Let's quickly look at the degree of freedom. You know, there's one thing I skipped the other. I said that it works with the degree of freedom determine the distribution, because there are different shape of chi-square distribution. Base is like a family. So the some group, if the degree of freedom is 1, then the shape is different from the one the degree of freedom is 2. Now, this degree of freedom, the concept is still the same. If you remember when we were summarizing quantitative data, we said that the degree of freedom is n-1. The example I gave there, for the benefit of those that were not there, what really happens is that the variable you are dealing with in the population, they vary. That's why it's vary. The value vary. Like age, even my weight, our age is not varying. You are every day you are 1 year older. Even your weight vary. Either it goes down, it's only that the age will not go down, it's going up. But the weight can go up and go down. So for any variable, they vary in the population, but their parameter do not vary. Parameter means the summary. Every age or every weight do not vary in the population. It's constant. Now, if you have calculated mean weight for a group of people now, that mean weight is representing, even though from your sample, is representing the population parameter. And anything you want to calculate after that, not all of them can vary. For example, the simplest example we usually give is that when we want to calculate the variance, standard deviation and variance, instead of dividing by n, you say divided by the degree of freedom, n-1. The logic behind it, if let's say you want to do, you have meeting, 5 people have meeting now, 5 people have meeting and they put 5 chairs there for you to sit. And the first person that attend will choose the chair, has liberty to choose, to vary. That is, his choice or her choice is independent of anything. He can choose from the 5 chairs. If he sit on one is not good, he will change it because it's the first to arrive. Nobody was looking. So after the person sits, the next person that comes, has choice to make from 4. The third person has choice to make from 3. The fourth person has choice to make from 2. The last person does not have choice. Not that, he doesn't even have that he doesn't have choice. So it's not a matter of the number of choices they have now. It's whether they have choice or not. You see, out of 5, 4, because the number of share is fixed for the number of people that are coming, the four people can make choice, can vary their choice, where they sit. Only one person cannot. That degree of freedom is. That is why it's 5 minus 1, since the total is 5. So that's why the degree of freedom is n minus 1. All the variables, all the values around can vary, except you get it further. It is the same logic for contingency table. The contingency table, you know that for the row, we know that you are dealing with it goes in 2 directions, the row and the column. The row is n minus 1. Look at it now. The total initially fixed, those blue areas is total. For 2 by 2 table now, the simplest example here, there are 4 cells. You know the total is fixed because you can, let's say I put the value of the total. So on the row now, all you need to know is to know the one cell. Once you know one cell, it's only one cell you can say, okay, if the total is 130 here, you can say, let this one be 90, let it be 70, let it be, it can be anything. But once you put a value there, this one cannot be, because the total, for the total to be valid, to be total, whatever is going to be here will be this, the first one minus this. So you cannot see, because the number of row now just minus 1. Then the number of column minus 1 also, because so for the row, the degree of freedom is the number of row minus 1. For the column, the number of column minus 1. So you now multiply the 2. 1 times 1 is equal to 1. That's why for the simplest form, the degree of freedom of 2 by 2 table is 1. 1 times 1. For this, look at the example here. If you change this 19, it's only one you can change here. It may not be the first one, it can be any of them, but once you just do one, the other you can fix in. Once the total are already fixed, all you need to put, somebody give you, once you know the value for 1. Just like in work problem, they say that you are dealing with 300 people, which 130 are male, 170 are female, 185 are employed, 115. If you want to just say 130 are male, you know that 170 are female. Then if they say 185 are employed, the remaining are not employed. They now say that if 90 people, 90 male are employed, finish. They now say you calculate, you automatically, you know that you remove this from one. So it's only one cell you need to tell you, because that's the one they can change the value, the other one fixed. They cannot tell you 90 and now give you another arbitrary figure and now say 50 if you add 90 to 50, it's more than 130. So it's only one set that can do it. Now, if is 42 of the, if you look at it, for 1 degree of freedom, it's just one situation, 2 by 2 table. That is simple. For 2 degree of freedom, there are 2 scenarios. It's either you have 3 row, 2 column, or 2 row, 3 column. And you see now? So the number of row, this and this, minus 1. The number of column, this and, can you see? So 2 column, 2 times 2 minus 1, this is 1. 3 row, 3 minus 1, 2. 2 times 1, 2. You say if they give the value, you will see. You know that the ones you know this, the rest you know. The same thing with this. For 3 degree of freedom, 2 possible ways also. 4 in 2 rows, 4 column, or 4 rows, 2 column. Degree of freedom of 4 that 3 scenario. 3 row, 3 column, or 4 row, 2 column, or 2 row, 4 column. No, 5 column rather. This 3 row, 3 column, 5 row, 2 column, or 2 row, 5 column. For degree of freedom of 5, 2 possible, 2 row, 6 column, or 6 row, 2 column. Degree of freedom of 6, There are 4 possible something here. 4 row, 2 column, no 3 column, or 3 row, 4 column, or 2 row, 7 column, or 7 row, 2 column. That's the way it goes like that. The implication is just why I even do that, because I've already said that the shape of the chi-square depends on the degree. That's why I try to explain the degree of freedom. And that's why when you get to where you look at the result also, it comes in. Can you see the degree of freedom is 1? Look at that red one. The degree of freedom is 2. This orange one. 3 is this blue one, deep blue. 5 is the green. 10 is the deep light blue. Look at comparing the degree of freedom 5, 10, and 15. Look at comparing 1, 3, 15, and 31. You will notice something that as the degree of freedom increases, the thing becomes like normal distribution. As the degree of freedom of chi-square increases, the chi-square will look like normal distribution. Now, you will now see, I'm just trying to show, to superimpose just like the other one. So if the degree of freedom increases, it's becoming flatter. Now, this one is an example of when the degree of freedom is 1 and the density function. Just like the way you know that the major part of the, for normal distribution, the major part that corresponds to 95%, the line or a point that separates 95% from 5% is where you take your decision. Because the level of confidence, 95% confidence, your level of confidence and the level of your significance equal to 100. If you choose 95% level of confidence, then you are rejecting no hypothesis as 5%. That is, your p-value should be at 0.05. It's a significant level, 0.05, which is 5%. So it's the same thing here. Of course, for normal distribution, the critical value where 95% meet that the other 5% of the graph, you know the total area is 100%. So the level of confidence is the bigger part of the graph, which is 95. The significant is the smaller part, which is 5. The standard normal deviation for normal distribution that correspond with that 95% confidence level or 5% level of significance for normal distribution is 1.96. Therefore, chi-square degree of freedom 1 is 3.84. So you can even look at it. We have already said that chi-square was derived from squaring standard normal deviation. For this degree of freedom, just square 1.96. 1.96 times 1.96 is give you 3.84. So the critical value, the value that corresponds with 95% confidence level for chi-square degree of freedom 1 is 3.84. For that degree of freedom 1. For degree of freedom 6 is 12.59. In fact, look at the table. Statistical table is here. The green part is the part that is corresponding with the level of confidence. The blue part is the level of significance. So look at the area, corresponding area for it here, green and blue. Look at under 95% confidence in that we usually choose, which corresponds with the 5% level of significance. The critical value for degree of freedom 1 is 3.84. For degree of freedom 2 is 5.99. For degree of freedom of 3 is 7.82. For degree of freedom of 4 is 9.488. For degree of freedom of 5, 11.07. 6 is 12.59, which we saw now, and 7, 14.06, and on like that. So I want you, before we go to hypothesis testing and do an example, I want clarification because I know that there will be need for clarification. Please, question, so that we do it. Welcome, Dr. Boluwoye. Dr. Ore, welcome. So I want clarification. Clarification, please. I know that there will be question and clarification. Any question? So that to not pile up, because this is a special group. I want you to have value for your money. Is it that it's so clear? Because if it's so clear, you know, there won't be question. But if it is so confusing also, there won't be question. So which of the option? So if you want to talk.
I have a question.
Okay, that's great.
My question still boils down to that the degree of freedom you mentioned.
Okay.
Because I wanted to know why, like how we work that, you know, as the degree of freedom is increasing, the curve is stretching out. I wanted to understand that relationship. Like, you know, those curves you showed, those different curves.
Yes.
Yeah, I wanted to understand that relationship. I know that the horizontal is the degree of what was the vertical? That axis, the
frequency.
What value was on
the
that
vertical
axis?
The vertical is the frequency. The horizontal is the, if you are telling you, is the chi-square value. The frequency means the many, if you do sampling distribution, which one has many of it in that group having that value. That is, if you do many study, many chi-square with the same degree of freedom, which one, maybe with 1 degree of freedom, no, with a particular chi-square value rather, maybe 1.7, and somebody that has 3, which one we will be commoner for that degree of freedom. So what is the shape? The shape, if you look at the initial, the one with the first degree of freedom 2, the initial value are high, then it's flatten half like that. It's telling you that more of the when you do take sample, more of the sample with that 1 degree of freedom, more of them will have smaller value. That's what it's saying. More of them will have smaller value. As the value increases, the frequency goes down. That's what it means. And the shape, as the degree of freedom increases, the shape look like normal distribution. You know, this one, that is why, if let's say somebody that has been following my teaching, my lecture since, if you remember when we gave introduction to differential statistics, one of the things we talked about is this central limit theorem that says that even something that does not follow normal distribution, even like this chi-square, all those, their sampling distribution follow normal distribution if the sample size increases. What we make, so one of the things that can point to increasing sample size is the degree of freedom. Because we know that the more, what you increase the degree of freedom is that when you have more contingency table. And when many cells will be appropriate when your sample size is high, you remember. Because you get to know that even chi-square will not be valid if your sample size is very small and you are now having too many cells. You are now having, that's why they ask you to collapse yourself. So those are the intricacies you get to understand. You know, if you understand bit by bit and you're able to marry what you learn somewhere with it will be sticking. It may be difficult for you to grab everything every day, but if you are following systematically. Somebody said this is the first time I'm understanding this code. Thank you. Thank you also. There any other question? Because sometimes if you don't want to ask question, you can type your question. Yes. Any other question? Any other question? Okay, we should proceed, right? Okay, let me proceed. So I'm assuming if you are not asking question, you understand everything is clear. If you don't want to ask question directly, you can type it. I will not make mention of your name that you are the one that asked this question. So I will just say somebody asked this, I will explain it. Please feel free. Okay. Let me continue. Let's continue. Now, let's quickly look at how do you now, let's start with this test of independence, the one we use. As you are going, you go to it, you click more. Test of independence. That is this Pearson chi-square. How do you use it? You know that it's an hypothesis testing. So in hypothesis testing, your null hypothesis and your alternative, I have already said it before. You either say that variable, null hypothesis say variable 1 is independent of variable 2. Independent means that it does not depend on it. No, we already said they are trying to use the word dependent and independent variable. So the one they are talking is maybe outcome variable is independent of this exposure variable. That is, sex has nothing, employment status has nothing to do with sex. Anemia has nothing to do with your location. Then another way of saying that's alternative hypothesis to say variable one is not independent. You don't want to say it's dependent, it's not independent. They are saying the same thing. So that's alternative hypothesis. Another way you can say, oh, there's an association between the two variables, or there's no association. Or you can even say there's a difference. If you want to use the word different, you are saying there's a difference in the exposure variable, outcome variable, rather, the one this person called variable one, outcome variable, between the different group of the exposure variable. Whichever way you state it, then we are testing the null hypothesis. And sorry. Okay. Now, if you remember, I'll come back to this one. If you remember, I said that the empirical chi-square, what it does is try to see this observed value you are seeing on the table. Is it different from the expected? We are trying to see if the observed and the expected are different. This way, I want to explain the concept of the expected value now. For you to understand. You know, I was saying the other time, observed expected value is the value when non-hypothesis is true. What is non-hypothesis? Non-hypothesis says there is no difference. In fact, let me tell you, for you to understand very well, you know the mean when you calculate mean value. The mean value is actually the value when non-hypothesis is true. If we are to we that are in this class now, if somebody want to say, what is the average age of these people that attended this class? And that's, oh, the average age is 40. Now, what did the person do? He had all the age of everybody. If we are 20, and now divide by 20, and now go that for. So that should have, if you are 120, so it's giving you something like maybe 4,000 or 400 or whatever. 400, you now divide by 20. So when you divide by 20, it gives you 40 or something like that, or 800 divided by 20. Now get 40. Now, that 40 is assuming that all of us have the same age. That's a value when all of us, you spread the age around the 40 people. If let's say all of them have the same age, what will be the age of each person? For example, maybe they give 5 of you that went for a meeting and they give you 100,000 to share. How do you share? Some people say, 20,000. Because it is you have assumed that all of you are the same. Have the same attribute, whatever what you want to use to share the money. If it is age, you say all of you have the same age. Or if it is rank, all of you are the same rank. That's why you share. But in real life, it's not like that, because when you go for a meeting, the HOD may decide to take half of the money. And then the next person that is senior can take more. So what is left for? So you may not share equally. It depends. But the mean, assuming that all animals are equal, all of you are the same. That is me. So that is, it's like not hypothesis. I usually give an example for you to understand. Imagine you have school now and your friend went to UK. Oh, I want my school want to do inter-sport. I want the jersey to come from UK. And the person, okay, when you got there, I want jersey for about 300 people or about 700 people. Now you now make up. What is the average age of these children you are looking at? You now say, what's the average age of your student? Now say, oh, let me call the head teacher. Now tell you, okay, 7 years. They will now bring jersey for 7 years, 300. You enter problem because they assume that all of them, average age is 7 years does not mean that all the students are 7 years. It's an assumption that all of them are 7 years. Can you see now? That is why, for that type of thing, it's not me you use. You better use mode. Now, so that's just it. So mean is the crudest model. Now, let's now come to the business for this one now. What expected value mean? Now, look at this example where we have 300 people, 130 male, 170 female. If you had them, it's 300. Or 185 employed, 115 non-employed. You had it's 300. Those are the total. Then how are they distributed? This is 4 cells. 90 male are employed, 95 female are employed. You add it together at 185. 40 male are not employed, 75 female are not employed. You add together, it gives you 115. Or you say 90 male are employed, 40 male are not employed. Add it 130. Or 95 female are employed, 75 are not employed. Whichever way. But this value in the middle is the one we are interested in. What you are seeing, when you do your work, you do your study, you calculate this, what you see. That is observed value. But if it is true that there's no, because if you do the percentage, no, I wanted to calculate the percentage. If you do the percentage, let me just to explain. Let me just peep and show you something. I want to explain the value. That 19. Sorry. What nonsense is this? Okay. Now, sorry, it's now sharing the one I'm not doing. I will not close. I think I will close this one. Give me a problem. It's intruding. Okay, let me stop sharing this. Yeah, sorry for that. What I want to do is that 90 May is 69.2% of the May are employed, while 30.8 are not employed. 55.9% of the May female are employed, and 44.1 are not employed. So what I'm just trying to show here is that you can see it's not just by looking at it physically. You can see people say, look, we have more people employed among female, but it's not true, because the more people are employed among men, because 90 out of 30 is higher than 95 out of 170. So if you put in percentage, you will see a proportion of the male that are employed are higher than that of female, and the proportion of the female of male that are unemployed are lower than that of the female. So whichever way, either you look at the total value or you look at the percentage, those are the observed value. Either you total value compare with the total, the value you have there compared with the total, or the percentage, that is observed frequency. But what is the hypothesized frequency? What is the expected? If the expected frequency is frequency when non-hypothesis is true, and non-hypothesis say there is no difference. There is no difference in the proportion of male and female that are employed, or the proportion of male and female that are unemployed. There's no difference. That means if there's no difference, there's no association between sex and employment. That is not hypothesis. If it is true, what do we expect the value inside those four cells to be? That's expected value. And the intelligent people now, okay, what we can do is that if that is true, the number of male that are employed should be proportional to the total number of male that in total number relative to the total. Look at it now. We have how many male do you have? You have 130 male out of 300. So how many people are employed? So the number of employment should be based on the total contribution of male to the total. The contribution of male to the total. So that's it. 130 because male 130 out of 300. 130 over 300 times 185 that are employed. It will give you 80. So we expect 80 male to be employed. For the female, the number that should be employed should be, because female contribute 170 to the total, 170 over 30 times 180 that are employed. It gives you 105. So we expect 105 female to be employed and 80 male to be employed. The same thing you do because the total that are not employed 115. So it should be contribution 130 male over 130 300 times 115 that are not employed should give us 50. While for female should give us 65. So we will look at it now, it will be giving the impression that more, if you expect more male to female to be employed. No, 105 over 170, if you divide it now and put 80 over 130, it will give you the same percentage. I want to give us everybody 1 minute to do the calculation. Please, I just give you 1 minute, give me the response. Please, the expected value for May is 80. Put that 80 over 130 and put 105 over 170 and tell me their proportion. Do that now and give me answer in 1 minute. Just 1 minute.
The first one is 0.6. The second one is 105, 170, 170, and 0.6. They are both 0.6. They are both 0.6.
Yes, both of them are 0.6.
They are both 0.6. Divided by
Have we done it? Have we done it?
yes, sir. 0.6 are both of them.
0.6.
Thank you. If you express it percentage, that's 60%, right?
Yes.
Yes, sir.
Yeah. So that is why they call it expected value. The value when you expect non-hypothesis to be true. That is, if there's no difference in the proportion of male and female that are employed, what are the count? What are supposed to be based on what we have here? What should the number? No, if you look at it, the total will still be equal, the same, like the old one, both sides, but the number in that cell will change. That is, this is how the distribution should be. It's like reshuffling that if this is the number that should be employed and this is the number that should be employed, because it should be based on the contribution of each of them to the total. So you percentage, if you do the same thing for the people that are not employed, it's the same. It's going to be the same. That should have equal proportion between male and female employed, equal proportion between male and female and not employed. That would be that you can now confidently say that employment has nothing to do with sex. There's no association between employment and sex. There's no difference in the employment rate between male and female. No hypothesis. So now, what test statistic does? Because I talk much about the origin of the test statistic. It's only I will not be, because I don't have much time to say it here. When I was talking about assumption around hypothesis testing, the people that were there, I received the lady, they will remember. I say all test statistics, they are the same. They are all the same. The logic behind it is this. You are looking at what you observe and what you expect. And what you expect is when the null hypothesis is true. So the difference between what you observe and expect, if that difference, is it much? If the difference is not much, that shows there's no difference between them. There's no difference. That shows, because what you are, the statistic you are quantifying is just something that will quantify the difference between the observed and the expected. If that statistic is very small, that shows that there's no much difference. That shows that, and the somehow the statistic now is interpreted with probability. When the statistic is very small, it shows that the probability, which is the p-value that corresponds to the statistic, the probability that the difference we are seeing as if it's different is just by chance. That shows that it's not a true difference. If the statistic is very small, the probability will be high. That the probability is high. This difference is the probability that the difference is by chance is so high. That is by chance. But if the statistic is high, that shows that the difference between observed and expected is high. The probability that is due to chance will be low. That is why the p-value will be less than 0.05. That is why the statistic and the probability move in opposite direction. It's only one statistic that is not like that. That's Mann-Whitney test, U test. Is when we are comparing mean, we talk about it. It's the non-parametric counterpart of student test. That one, as the statistic increase, the p-value increase as well. So that one is usually not. So for it to be significant, the statistic has to be small. That's the only one. Every other statistic, either chi-square, t, other t-test, ANOVA, think of any hypothesis test, you expect if it's going to be significant, the statistic should be high and the p-value will be low. So that is why the intelligent people now say, okay, since look at the way we calculate the expected value now. The intelligent people now say, look at it, just say, if you don't want to stress your brain, just say row total times column total divided by grand total. Grand total is the total at the corner. Then the row total. So for each cell now, this cell that has 19 now, what is the expected value? Just say 130, which is row total, times column total is 185 divided by grand total. Look at this. It's not 130 times 185 divided by this. The same thing for this one, for this female that I employ. 170 row total times column total 185 divided by grand total. It's not the same. 170 times 185 divided by this. The same thing for each of them. This one 130 over 115 times 130 times 115 divided by the grand. It's not the same. This one row total is 170 times column total 115 divided by grand total. They, you know, when they ask people what is the expected value, row total is, you don't know the logic behind it. Though sometimes the intelligent people usually create mnemonic for people that don't want to think, so that fast, you just put it. At the end of the day, the thing will lose the value and people will not know. It's good to remember the mnemonic as well in the exam, but sometimes it's good to even know the logic. When you know the logic, it doesn't budge you. There's no need for cramming. So some of these things, they are logical, and it's people, it's not as if the formula comes from heaven. It's people that have tried to model life situation and now put it. And that is why we have problem today. You see that people teaching mathematics and statistics, they just be solving theta, this. But the issue there is that it's not the theta that comes first. It's the real life situation that some people okay, model. But when you begin to teach the model, and when you cram the model, then try to fit it, so it doesn't allow people to think. So now, look at that formula now. The observed minus expected. But the logic, you see something. Look at this. Look at for each of the cell now, 4 cells, we put the observed minus expected, observed minus expected. You notice something. You come to this second row, you see when you look at the difference, it appears to be the same, but half of it carry positive, half carry negative. If you didn't square it, if you add them together, it will give you 0. And I explained this when we're talking about summarizing quantitative variable, quantitative data, when you wanted to calculate variance and standard deviation. When you, they have calculated the mean. You want to know how far each is deviated from the mean. Now calculate, you remove mean from each value. When you remove mean from each value, because that mean is a middle value, some will be lower than, as much as that are lower than the mean are also higher than the mean. Those values that are lower than mean, when you remove mean from, it give you negative value. The one that have the same value as the mean, it give you 0. The one that have much more value than the mean give you positive. If you try to add the deviation, it give you 0. So you cannot do much with deviation. That is why the intelligent people now, let's square it. Mathematically, when you square minus, it positive plus. That's how they were able to go further. It's the same thing here. If you just had the difference between observed and expected, you end with 0. So you now square it. When you square it, you still want to quantify the difference between you square it. It will make sense to divide by expected because you have squared it. To remove that square from it. So it's like you go one further. That is why when you calculate variance also, the variance does not have the same unit as the mean. It's only the standard deviation, because in process of calculating variance, you square the deviation. So for you to have something, that's why the variance does not have the same unit, because the variance will have a unit square of the mean. So for you to have unit the same with the mean, you calculate the square root of variance, which is standard deviation. And that's why you quote your mean together with standard deviation rather than the variance, because they have the same unit. So it's the same thing here. So intelligent, okay, let's square it, then let's divide by the. So when you now do that now, it gives you everything positive. You've already said that chi-square is not negative, is from 0 to, it doesn't have negative value. It's because of this square issue that eliminated it. So when you now add it together now, look at this, the value is 5.5269. The critical value, if you remember, for one day, you know the degree of freedom is 1, because number of row is 2 minus 1. Number of column is 2 minus 1. 1 times 1 is 1. So if you go and look at the critical value, the corresponding critical value for degree of freedom is 3.84, which you have seen before. So your own chi-square value is higher, so it's significant. That shows that the corresponding p-value will be less than 0.05, since the chi-square is higher than the critical value. If the chi-square now is lower than the critical value, the corresponding p-value will be higher than the 0.05. That shows that it's not significant. But you cannot calculate p-value, because before computer came, you have to go to that table. That table I showed you before. Now look, okay, what is the degree of freedom 1? What is at what level is 0.05, 95% confidence? Okay, what is the critical value? 3.84. Oh, our chi-square is more than 3.0. Oh, it should be significant. That shows our p-value will be less than 0.05. Thank God for computer, it brings the result out for you. It will give you the p-value. You will know that this p-value is less than 0.05. You don't need to go and be looking at the table. So the table is no more useful. But it's just good for academic purpose, for you to know the logic, the reasoning behind it, and how the old people suffer before computer. Now, I don't know if there's any question. I'm going to run. Okay, maybe before we run it, let me just think. Well, okay, let me explain. Now, when you calculate the chi-square like this, the Professor Yates believed that for 2x2 table alone, that's the simplest one you can have. That the formula tend to overestimate the statistics. That is give you big chi-square more than what's supposed to be. So in that way, something that wouldn't have been significant, it may tell you that it's significant. So you now bring in correction. And because you know that a chi-square is said is a continuous probability distribution, which is being used for categorical to test association between categorical variables. He believes that that smallest contingency table, which is 2x2, need to give some correction. And the correction it does is to, anyway, before I talk about the correction, so the reason, number one, 2x2 table, but unfortunately, many people say that is correction over correct this thing. Typically, the degree for you to do the correction, of course, I've already said the degree of freedom must be 1. That is 2x2 table. 2x2 table is like saying the degree of freedom is 1. Expected frequency should be less than 10 in at least one cell. Look at it. That is expected frequency. You know, we have talked about expected frequency now. So the one we expected value is not the total tree, it's not the observed value, it's the expected. Sometimes your expected frequency can be 0. In your observed frequency may be 0 in a cell, and expected frequency will have a value greater than 10 or greater than 5. So many people don't know. When you submit your result, they say, when they see a small value, okay, they now say, look at this value at less than 5. No, it's not the observed value, it's the expected value. But though when some frequency are small, it may be a pointer that some expected frequency may be small, less than 5 or less than 10 or whatever. But it's not absolute. It may be a pointer for you to check. It may be pointing to is the expected value. The expected value can be, the observed value can be small, and the expected value can be greater than that. Then, in at least one cell, the expected frequency should be at least 10. But some people say no, it should be at least 5. And you see, some people even say that which year correction, that thing even overcorrect that. Even chi-square is a conservative test. You don't need correction. So if an issue of create correction, there is division among statisticians. I myself, I don't even believe in that correction. But people use it to their advantage. I will tell you when we run the result, you see how people use it to their advantage. So how do they do the correction? Let's look at the correction. The logic, what you just do in that formula, can you see? In that formula, you now remove, when you remove observed minus expected, before you square that difference, you remove 0.5. That's the correction you put in the formula. That's all. And it's an absolute difference. It's not mathematical difference. You know, if it's mathematical difference, if you say minus, minus, both of them, you have to now, first of all, add the two together before you minus from the other one. No. You have to first of all minus that difference first from this one, and now minus from that one. So it's the absolute, because irrespective, if you know the reason being that some you've seen before, half of the cell we have positive, half we have negative. If care is not taken, it will give you different value. Look at it, we did the same thing for this one. Can you see they still carry the same value here? Because what you do is to first of all say, okay, the 9.83 plus here minus 9.83 minus 9. So if it is mathematical different, if this one minus 9.83, you now say minus 0.5, it will give you minus 10 point something. But it's not like that. It's absolute different. You, irrespective of the sign, you remove that 0.5 from that difference. Either it was negative or positive before. It's not your business. Neglect the sign and remove that. That is why all of them are still carried the same. You know, it was before you get corrected, it was 9.83. It's only sign that make them different. So when you remove 0.5 from 9, it gives you 9.33. All of them same 9.33, irrespective of the sign, before you now square it. That's why when you see slash like that, it means absolutely different. It's not mathematical different. So you just know that. And when you calculate it, you see the chi-square is smaller than the other one. The other one is 5.55, but this one is 5.002. So that shows that if, let's say, that shows that the other one is more significant. So the implication of that is that if, let's say, that original Pearson chi-square is close to the critical value, maybe it's around that 3.84, which is exactly significant. This one will be less than 3.84. It will not be significant. Now, so this is another way of writing this yet corrected in order to remove decimal, the effect of decimal, mathematical way. There is a complexity where do all these things just for you to get the logic. You are not going to be calculating unless some of you, when you are doing your masters or see cry, want you to calculate. Me, even if you are doing masters, I will not be asking you to be calculating anything. I would rather ask you how you use ask you some logical question, then how you use SPSS to run it. That's just it. But we are different. So this one is an alternative formula. They just do some change of formula to remove negative effect, and it gives you the same thing. So look at the same data set. So we are going to run it. You're going to see all these results. The likelihood ratio chi-square. Now, because what I'm explaining them, when we run them, all of them will come out in the same data set. Now, there's something that is very important here. It's an alternative. Intelligent people, they know how to play with number when they think. They base this logic on what they call maximum likelihood theory. The idea is when you just collect some data and create a model with the probability of obtaining the observed data set is maximized. Then you compare this model with the probability of obtaining those under the null hypothesis. But just leave that one. I will explain to you with the formula down. The formula is saying, you will see one logic. You understand the Pearson formula, observed minus expected square. Of course, actually, the logic behind is observed minus expected. The difference between the observed and the expected. That's all. But because we know that if we just do add it will be 0. Intelligent people, let's square to remove it will be yes, it will have, because there are as many that are positive and negative. Okay, let's square it. So in order to cancel the square, let's now divide by the expected to cancel the effect of that square from the result. So it's just a difference between expected. So just like the way when you do your arithmetic mean, because you say in some situation it's not appropriate to do arithmetic, let's do geometric mean. It's the same here. These people, instead of say observe minus expected, this model you are seeing here is, as when you say model, is the expected. Sorry, it's expected. No, I was telling you when you say observe model, hypothesized values are model. Now, observe minus expected. You know, if in logarithm, the corresponding mathematical operation for addition in arithmetic is multiplication, while the corresponding for division is, for subtraction is division in logarithm. So, you know, in the other one is subtraction, observe minus expected, and that's observe divided by expected. Can you see now? Observe minus divided by expected. So when they do it, it's just to do natural, ln is natural logarithm. Observe times observe. If you look at it, it's like opposite of the other one. That one remove observe from expected, expected from observe, that is observe minus expected divided by expected. This one I say logarithm of summation of observe times. Can you see now? Instead of dividing by the expected, it multiplied by observe. Then instead of removing observe from the expected, it divide the model expected from the observe. They just do logarithm. They just go. They did the same operation using logarithm. That's all. So he give you a value. Look at it. Almost the same thing, but it's slightly different from the other one. If you look at it, it's not far from it. The other one is 5.55. This one is 5.56. The same. So normally the difference will just be small. So you don't need to crack your brain. It's not for you to know how to use using to do it. Look at the result now. Summary of the 3 results. Can you see this one? This one. In fact, the p-value when we run, you're going to see the p-value for Pearson and this likelihood ratio is the same. This one that just small, slightly different. It's corrected. Now, before we run now, the last thing I want to say, because all of them will appear in the result. That's why the last one I will say before we run is Fisher exact test. If you remember, there are 2 lines I omitted for condition. The condition for using chi-square. Now let me go there, because the reason I didn't want to say it is because we've not discussed expected value, so that I will not bite my tongue trying to explain. Look at this number 4 requirement for using chi-square. Relatively large sample size, expected frequency for each cell are at least 1. That is, there's no expected frequency that should be less than 1. Please, this one is different from Yates corrected. For using Yates correction, we say that it must be 2 by 2 table, and the expected frequency should not be less than 5. Some people say not less than 10. Some people say you don't even use it. So since even statisticians are confused about that one, the condition for Yates is not so stringent. It's only if your examiner or your teacher is Yates correct. I will tell you the way people play on this when we run the result. I will tell you the way you play some people intelligent in interpreting the Yates. But here is if for using chi-square, even on its own, forget about chi-square, pressing chi-square, the expected count should not be less than 1 in any cell. That's why I say frequency, the expected frequency for each cell should be at least 1. Then the expected frequency should be at least 5 for the majority, 80% of the cells. That's where that shows that it can be less than 5 in 20% of the cells. That's what he's saying. It should be at least 5 in 80%. That is, it can still be less than 5 in 20% of the cell. So that is why when you now run your chi-square, and the expected in your own table, the expected count is less than 5 in more than 20% of the cell, or is less than 1 in any cell. These two statements now correspond with what are written here. When the expected count is less than 20% is less than 5 in more than 20%. Look at it. Expected count should be at least 5 for majority, 80% of the cell. That is, can be less than 5 in 20. So when it is more than 20, that shows that is the 5, at least 5, not up to 80%. Then you should not even see any expected count less than 1. So when you see any expected count less than 1 in any cell, forget. And I think it's well understood. Let me go back to that table now. Yes. So now, if it is 2 by 2 table, one cell is 25%. So when you even have any of these violation in any one cell here, if you have expected count less than 1 in anywhere, we have already said that. But if it is less than 5 in one cell here, because one cell is 25%, it's more than 20% violated. But if, let's say, it sees the 6 cells now, like 2 by 3 tables, 6 cells. If the expected count is less than 5 in one cell, the one cell out of 6 is 16.7%. It's not up to 20%. It's still okay. It is when it is 2 out of 6, which is 33.3%, that one is more than 20%. Those are the things that many, even some examiners, they don't know. When they just see it, I can see, they see expected count. Even some of them, they don't even know. They just look at the observed count self. Even if they calculate the way they see in one set, they say it's not bad. No. But any contingency table, when you see expected count less than 1, forget about chi-square. But for less than 5, it has to be when you have more than 20% of the set. So more than 20% of the set, 1 out of 2 by 2 table is more than 20%. For 6 cells, it has to be 2 tables, a 2 cell before it can be more than 20. 8 cells. So when you calculate that, so 1 cell in 8 cells, one cell in here out of 8 cells will be around 12.5%. Can you see? You take 2 cells, I will give you 25% for you to say it's more than. Can you see? For 8 cells. So like that's how to interpret. So whenever you encounter this, it is better to go for Fisher exact, because Fisher exact is not a statistic like chi-square. It's a direct probability. All hypothesis tests, we have statistic and the corresponding p-value. But this one doesn't have statistic. It just have p-value calculation with one rigorous formula like this, factorial. You don't need it. Just with this one. In fact, this one is even for 2 by 2 table anyway. It's just for you to know the concept. It's probability they calculate there. So you now go for that exact. That's the summary. So we want to run that is why I give this data I'm presenting here is part of what I sent to you. So before we want to run the data and close for today. We run the data and explain the result. We close. We continue tomorrow. But before we do that, I want to ask question. A clarification from what we've just discussed before we run the data. Any clarification?
Thank you very much, sir.
Yeah.
I just had one clarification.
Okay.
The part about, where you talked about the statistic and then the probability.
Yes.
You said that if the statistic is if the probability is usually very high when the statistic is. I wanted to if you could just explain that part. Like I have, and I know what you're trying to say, but I wanted to just say it again so that I'll just, thank you.
So you just know that the probability and the statistics move in opposite directions. That's just it. The probability and this, it's only time permitting. What's the time now? Okay, let me just explain, because a lot of things, in this type of it's just like you, if you are in university or you are in a particular class, you believe that you have passed one class before you come. If you have not passed the class and you have not passed the class, you believe that nobody will be feeding you with this thing. So some of these concepts of p-value, all those I've explained it before. Now, the p-value is the probability that this difference I'm observing is due to chance. Okay, let me just, the table we are looking at, let me just, because it's good for you to understand it very well. Look at, we have already said with this or our observer, look at the table. The observed value, expected value. The observed value, that is what you summarize in your study. What you get as observed value. But it's very obvious in this observed value that more men are employed than women as by percentage. It's not the absolute value. When you are talking, it's a relative issue. It's more from what we are observing. More men, your research shows that more men are employed than women. That's what you observe. So, but this thing can be, if you do the result and do the study, another person can do, you can get another result that it's not like that. You want to go and put it to test that this is what we are testing. Now I put it, say there's no whatever, there's no difference. Whatever observed value it's just chance. Whatever observed value you are seeing, that you see in your data, it's just chance occurring. There's no actually different. So, and I've already said it before. I said when we're discussing inflation statistics, the probability of committing type 1 error is the p-value. Because type 1 error said that there is a difference when there's none. Rejecting no hypothesis when it is true. That is, no hypothesis, because if it is, you find it different, you reject, I reject you, there's a difference. Because one no hypothesis say that there's no difference, don't go your way. But if you find it different, you say, I reject no hypothesis, there's true. But there's a probability of you rejecting no hypothesis when it is true. When there's no difference, you say there's a difference. And that is the p-value. Also, another way of saying it is that the probability of you saying there's the probability of the observed difference being by chance. At least if it is by chance, that shows that it's not a true difference. So if actually there's a difference, there's an association, the statistic value will go up, but the probability that is due to chance will be small. Does it make sense now? If there's a difference, really different, the statistic you calculate, the value will be high to reach a critical value and even go above. That should your probability of saying this result is just a chance, so there's no difference, it's very small. And that's what you are testing. Also, when your probability that this is due to chance is as small as 0.5%, that is 1 out of 20, 5 out of 100. You want to say that probability is small, that I don't think it's due to chance, so it's a really different. And by that time, your statistic is high. But if your statistic, if there is not going to be any difference, your statistic will be small, because that's looking at the difference between the observers, but it will be small. And your probability that this difference due to chance will be high. And that shows that if your probability is due to chance is high, whether it's 0.05 or it's growing high, maybe 0.77, as it's growing high, that should have forget. Whatever difference you are looking at is due to chance. Do you see the logic now? And I've already told you that's how all the statistics work. The only one, Matt Whitney, you test. In that case, you expect this, if it's going to be small and the statistic will be small. That's the only one.
Okay.
Any other question? Any other question? No question, right?
I have a question, please.
No question, right? You have the question.
I have a question.
Okay, go on.
So, when you talked about the expected values,
Yes, ma'am.
And the observed values. These assumptions for chi-square and Fisher's exact, is it for the observed values, the cells, or for the expected?
Expected.
Okay, so if you're running it with a software, you won't see the expected values.
You will see, don't worry, we'll tell you.
Results will just come out.
We'll run it, you know, there's a, you click, if you need it, you click on it. I will do it now. If
okay, so my question now is, if you have a set of values you want to run, so how will you now know that it is chi-square or Fisher's exact that is suitable when you want to use a software?
You have already, you see, okay, don't worry, you are jumping the gun, because when we are running it, it gives you, in case you want to, it give provision for it. It's just like if you are going somewhere now, you carry your water bottle in case you need, you carry your umbrella in case it rains. You understand me now? So when we are clicking on it, it gives you provision. You want to know exact, the Fisher exact, there's a place you click on it, we want it to run for you. And even apart from you knowing the expected value, even the result also, the people that program SPSS, they have already put it there, they alert you. If the expected value is more than, you will see it. So all this your question, when we run it here, we answer. It's a question that will be answered.
Okay, thank you.
Okay. Any other question? Should we go on to run it now? Okay, it is clear. Now, this who downloaded, who has the data file? Who has the data file? Who has the data file? This who is Uju? Who is Uju? Who is Uju? Uju, who is Uju? Unmute yourself. I will remove you. Who is Uju?
Hello.
Hello. Yeah.
Can you hear me?
Yeah.
Okay. Would you? That is. I spoke with you yesterday. Before you forgot.
Oh, is it okay, Dr. Obianuju? Oh, sorry. No, that's sorry for that. You will just say no, Nechebe. No, okay, because right. It's just like
I joined.
Yeah, no, I joined you. I want to be I want to be sure. I want to be sure of.
Yeah, that's fine.
Because for security reasons. Because I didn't lock the door.
It's okay. It's fine.
Yeah.
Sorry, I had to join late. I just came.
Yes, you said it yesterday. That yes, yeah. So, so should we go on to? Do we go on to run it now?
Yes,
who has the data? Who has what do I call it? It's not me that will run into. It's one of you that will run it, so that it can be as practical as possible. Because it's me doing it now. At least I've done all the talking. You didn't run it, but I will tell you what to do. So whosoever have the, what do I call it, SPSS installed, and you know where you store that data file. So I want you to just click on your SPSS. Who will do that for you? You first of all open your SPSS outside the Zoom. Immediately it open like this. Just, I will allow you to share. You now share. I will allow you to share. You click on share on the Zoom. When you click on share, you now go and double click on the SPSS. Everybody will see it. I will tell you what to do. Who will do that for us? So that is part of the learning. You see that? Who will do that? I'm sure Dr. Kayode, you have known, because you have not installed your own. I know Dr. Boju is ready.
No,
right?
No, sir. No, sir.
You are not ready. What of who has Dr. Bako? Have you installed your own? You have it?
Which of the files are you talking about?
Okay, Dr. Olago, you want to? Okay, thank you.
Which of the files?
Yes, socioeconomic status class, socioeconomic class. So Dr. Olago will do it for us now. Don't go and open. Just open the SPSS first before you share it. Share the SPSS interface before you go into it, so that people can see the way you did it. You are doing it. You click on the SPSS, then share with us. So you can share. Just click on share and double click.
Okay, please. Socioeconomic status. I can't find that. I can find Kappa, hypertension, lung cancer.
No, it's okay. Okay, socioeconomy, a sec. There's a sec. You are looking at the old one I sent to you. I sent you within that. Don't worry, but it's the same thing. Go to sec. There's one called sec. SEC. When I SEC, can you see it? There's sec. SEC. You didn't see SEC. Okay, please, who downloaded what I gave you? I don't want to run it. I want you to run it. Who is? You did, Dr. Olagio, you didn't see the sec? In the old one, the one I sent to you, say you see Kappa, there's sec. You didn't, that way you didn't save it. Who else? Dr. Bako, did you? I think you have SPSS, right? If you want to talk to me, you have to unmute yourself because I will not hear you if you don't unmute yourself.
Okay. I haven't downloaded it yet.
Okay.
That's what I'm doing now.
Okay, Dr. Raymond.
So it's still,
Dr. Raymond, open your SPSS.
Hello, sir. Sorry, I just want to find out something.
Okay.
What version of the SPSS are we using?
What version is 20? 20 I sent to you that I said you install. No, don't worry. Have you installed it that time? I thought you removed it.
No,
Did you install it?
you have not given me. I just want to know.
No, I sent to you. I said, immediately I mail it to you now. I said that you may not be.
Okay, it's in my mail.
Yes, don't worry. Do that after this evening lecture.
Okay, sir. Okay, sir.
Yeah.
Okay. What version, sir? What version?
20 and the step. Dr. Afefi, okay. You say I didn't send to you? I think I sent to you, Dr. Afefi. Your email.
So I didn't receive anything. I didn't receive anything on my mail.
On your Gmail?
No, Yahoo.
Okay. If you even Yahoo, you may not even be able to. I think I sent it to you. I send it. You may not be able to download it. You don't have Gmail. That was why I was asking for Gmail. Don't worry, I will check.
Okay.
I will check immediately.
I will send a Gmail. I'll send a Gmail.
I know I asked for Gmail. Send Gmail.
Okay, I'll send a Gmail, sir. I didn't receive any material.
Okay. Dr. Andrew. Okay, somebody has opened it. Who is sharing with us? Who is sharing now? Hello. Okay, it's Dr. This is Dr. Olagunduri. I know. Okay, you have gone to open it anyway. I want them to say, okay, no problem, by tomorrow. So now, open the click on the data view. This is SPSS, this is variable view. Click on the data view. Let people see it. Click on the data view. This is where the data is. I believe everybody, because we did a training 2 weeks ago, 2 batches also on how to go about SPSS. So this data view, you can see this is sex, employment status, education, socioeconomic status. So we want to, the example we look at is employment status and sex. That's what we use to calculate all these things. That's what we do. So, and we have already, though we coded it, anyway, you go and be checking that one. Click on the view, let them see the coding. Click on the view map. Click on the view so that you go. Click on the view on the top. No, view. No, we have to go back to that data view. Data view. Then click on the view. Yes. Click on value label. So can you see now? It's just showing you can decide to off it or on it. We have coded male 1, female 2, and employer 1, unemployed 2. That's what we coded. Okay, that's not the issue now. So now we want to analyze. Chi-square is a non-parametric test, but the only one you go and do in non-parametric test is the chi-square. Tomorrow we look at it, chi-square of goodness of fit. But most of the time is you go to analyze and go to start. We'll do it now. Analyze. Click on analyze. where you see chi-square is analyze. Click on it. Then you now go to descriptive statistics.
Please, I'm also following your. I'm also doing the same thing, so I'm just trying to follow as well.
No problem, but you be fast if you are following, because you will not delay us. So be fast, as this person is, you know, this one is showing everybody. Everybody is looking at it, even including you want to look at it. So everybody is looking at it here. Everybody is looking at it here. So it is under the script cross tab. Click on cross tab now. Click on it.
Okay.
Now it will open you this dialog box. So you will see that it gives you row and column. So we have already said our exposure. We are looking at association between sex and employment status. So which one is the exposure? Somebody should just quickly tell me. If you want to say talk, you have to omit. Sex is the exposure, yes. So the sex will go to the row. Sex. Yes, go to the row.
Okay.
And the employment status go to the column, which is the outcome. Go to the column. That's great. Now, you will see statistics, some options on the left side. Click on statistics. The person that was asking about Fisher exact, this way. Okay, wait. Let's do it one. Okay, it's okay. Click on statistics. Click on chi-square. You know, you can see a lot of things you can do here. Even kappa, risk, many things you can do here. Even McNema is from here. Anything categorical you cross tab. Anything that has to do with cross tabulation is here. Is where you see it. Then please continue. Chi-square, that's what you want to know about. Chi-square as statistics you want to calculate. Click on continue. Okay. Click on exact. No, you can first of all click on it. Also click on exact. You see, when you click on exact, this is where you calculate your feature. You include your feature exact. By default, you see asymptotic. Then you see Monte Carlo. You see exact. Click on exact now. Yes. That it also see exact. Click on exact. Yeah. Then click on continue. So can you see some of the Dr. Raymond? This is where you exact. Then click on cells. So he was asking for expected value the other time. Click on cell. By default, you click on observed value. That is, it will show you the observed value. But if you want to look at the expected value, which may not, just click on expected. It will also give you the expected value also. Yeah. Then under percentage, click on row. This is where I want you to, if care is not taken, if you don't know how to put your row and column and know how to click. If let's say now, I want to run this in. Why I click on the row now is because we have put the exposure as the row and outcome as well. If by maybe we did the other way around, I will click on column instead of row. You know, there are some situations where you do it the other way. You know, sometimes when you want to arrange your result, you want your result, you do, because more your foolscap sheet, the paper you use is A4, the page you use, the portrait, you have along the vertical a lot of space, there along the horizontal no much space. So if your outcome, if your exposure have many row, it's okay, and your outcome is just 2 categories, it's good the way we did it. But there are some situations, some people, their outcome variable is the one that has up to about 5 categories. The exposure is sex, which is 2 categories. Can you see now? So they don't want to put many things. They don't want to put the outcome along the vertical. They want it to be along the row, and the exposure, which is 2 sex, along the vertical. But you have to change your percentage, otherwise your interpretation will be wrong. Okay, we'll look at it later. Okay, click on continue, ma'am. Click on continue. Continue. Have you done that? Click on OK. Then share with You know, it will not show all the result view unless you share. So share, second share the result with us. It's not sharing you. Second share. You double, yeah, great. So scroll down. Scroll down. Great. Yes. Can we see the result now? This option. No, scroll down so that I can show us here. It's the last two tables I want to see. Yes, it's okay. No, still scroll down. Yes, it's okay. Yes, okay. It's okay. Now let's interpret the result now. You will see the same 2 by 2 table, male, female. Look at the expected value, 90, 40, 95, 75. Look at the observed value rather, 90, 40. Then look at the expected value we calculated the other time, 80.2, 104.8, 49.8, and can you see the expected value also? If let's say we didn't click the expected value, it will not give it to us. Then you don't actually need to put it anywhere unless you want to check anything. You know that even when you are in an exam or you have already gotten your result, you don't need this row total times column total. It will give you the expected value if you want to check. But you, of course, you are not even entering your expected value in your result, so you may not click on it. It just show you. So you look at it. Okay, let's now go to the Pearson chi-square. Can you see the Pearson chi-square we calculated? Is it not the same 5.53? 5.553. If the rate corrected chi-square 5.02002. Look at the likelihood ratio chi-square 5.609 we calculated. Look at Fisher exact test 5.534. The only one here we didn't calculate, we don't need is linear by linear. By the time we get for chi-square for trend, we will use that linear by linear. But it doesn't make sense here because this is a 2 by 2 table. You know, this chi-square for trend is also go for log linear analysis. You know, the computer will just put in a lot of things. Which one will be? So now what we need is 1, 2, 3, 4. We may need. So, but nobody, most of them, nobody use likelihood ratio. But you look at it, the same p-value for Pearson chi-square and likelihood ratio chi-square, the Pearson value. But most of the time, when they talk about chi-square, they mean Pearson chi-square. The Yates corrected, you will see that it's significant also, but it's not as significant as the Pearson chi-square because the p-value is higher than that of the, but it's still significant, less than 0.05. Just like the way the value of the statistics is lower than the Pearson chi-square. So what I wanted to say about this Yates, the politics many people play with is that the way it is significant, both of them are significant now. So many people say Yates corrected, they put Yates corrected because they don't want to examine or anybody to say, is he Yates corrected? That's yes, Yates corrected. Don't ever tell that because these people, they can use TACA, they can use WinPepi. There are some statistical calculator which I share with some people. Just we don't need it now. They can have your book, even without your data on your table, they can enter and calculate the chi-square. You will get the Yates corrected and get the Pearson. If you are saying, is it Yates corrected? You know, some people, they are looking for something to fail you. They say you tell lie. So that's why many people, since both of them are significant, they put the Yates corrected chi-square because they don't know the type of person they are meeting. But let's say if the chi-square was just barely significant, maybe the chi-square was 3.84, which is the borderline, and it just exactly 0.05. The Yates corrected chi-square will be less than that. It will not be significant. So they will not choose the Yates corrected. They will choose the normal chi-square because if they want it to be significant. Unless if you don't want that thing to be significant, when you now see that the Yates corrected is not even significant, you now choose the Yates corrected. So that is the way people take their decision. You know, people can tell lie with statistics. That's how to tell lie. And many people that change because change data file, all of them contribute. Now, that one is that. Now, let's come back to this table. The table, that table, male, female, you can see. You will see 69.2%. That was what I calculated. I said 69.2% of male are employed. 55.9% are also employed. So it shows you that in your interpretation of the result, you now say, oh, more of male are more likely to be employed, 69.2% than female. And the difference is was statistically significant. Now put the you can just put the p value because chi-square on the table. When you are writing your result, oh, the male are more likely, 69.2%, to be employed than female, 55.9%. It shows that the percentage of male that are employed more than that of female that are employed. Now, for you to know the importance of which total to put, let's go back. Yeah, analyze. I want you to now put column percentage also. You see what will happen. Go back, man. Let's run. Go back. Analyze. Just click on analyze here now. Analyze, descriptive, cross-tab. No, not descriptive, cross-tab. You didn't cancel. Cross-tab, yes. Now, all you need to do, just go to that cell. Click on the cell. Everything is already there. Click on the cell. Then, no, it does not click. It does not show us. Click on the cell. Okay, yeah. Click on column also, column percentage. Click continue. So it will show us both row and column percentage. Click continue. Okay. Okay, click on OK. Okay, scroll down, remove this thing, yes. Why I allow one of us to be doing it so that it will not say it's me that is doing it. So you can run the same thing. So you will see this table that because we show row and column percentage. Look at if the other time we say the first one within sex, the second one within employment. The first one, that was the one we showed along the row, is telling you 69.2% of male are employed. But this one is telling you 48.6% of employed are male. It's a wrong interpretation. You are not interested in the number of the exposure that come out of the outcome. What you are interested in is the number of proportion of the outcome that have a particular, in the proportion of the exposure rather, that have the particular outcome. You are not interested in the proportion of the outcome that belong to a particular exposure. You are not interested in the proportion of people that are employed that are male. If you look at it, if you go and interpret it like that now, you make mistake. You see here now, 51.4% of the employed are female, right? That's what this one is saying. 48.6% of employed are male. It will give you no impression that, wait, we have more of the female in employment, but you are forgetting that we have more female in that population than male. It's just like if you are trying to look at the employment, social, geopolitical zone in maybe in federal government employment, what is their federal character? Somebody will say that, can you see the percentage of these people that are from northeast? Can you see plenty? But if you really want to know, you have to know the population in each geopolitical zone and now know what proportion of those population are there, rather than say the outcome and now know the exposure. Can you see that? So you can misinterpret. So that is why you must be able to know which one is your exposure variable, outcome variable. And when you are entering it into, you are running the analysis, which one should be the row and the column. And when you are now putting your percentage, you move, if you put the right thing, you roll as the exposure, as the exposure, yes. Your percentage should be along the row, along the exposure. Your percentage will be along the, so you say, out of this total number in my exposure, this is the proportion that have this outcome. That's where you can compare. If you look at the first one now, 69.2% of the male are employed, compare with 55.9% of male female. It shows you that more male are employed than female. If you look at the proportion that are not employed, 30.8% of male are not employed, compared with 44.1% of male. It shows that less number of male are unemployed. So I don't know if there's any question. Can you see all these concepts now? Pearson chi-square, yet corrected, likely, forget about likely ratio, Fisher exact test, those issues, you have ironed them out. So when you are running your analysis now, if it is 2 by 2, we're going to run maybe by tomorrow. When you run, okay, maybe, okay, no, by tomorrow, if you run, okay, let's run, okay, let's run Ugo Naya, Ugo, Dr. Ugo, you have to share your own now. Share your own with us.
Okay, so the way my own is, so because I'm using my phone. So
you are using your phone?
I didn't use my laptop, yeah.
So is your phone you are using to run the analysis?
No, I have my laptop. Can you see my laptop?
And why are you not using your laptop? Okay, who else is where?
Okay, like I should have done Zoom, like I should have been doing it on this laptop. I knew it too late. I discovered it.
No problem. No problem. Who else will share? I want another person to run that next one, not Dr. Lagujue. The more the person does, the more the person knows it also. Who else can share our own or his own?
Okay.
Who else?
Okay, because I already did it on my laptop, on my own.
Who else?
I think I can share. I can share mine.
Okay, share your own. Share your own, the same file, the same socioeconomic status.
Economic status.
Yes.
Okay.
So share with us. Let's just run the last one and we'll talk now. I just want you to see that once it's not 2 by 2, there's nothing like year correction. That's just what I want us to see. Okay. No, why are you going to data? It's okay now. I thought you have shown it. Is that not what we are seeing?
That's blood group. It's not the one.
Okay, that blood group. Okay.
Yes.
That one is for goodness of it.
Yes.
So see the way it's doing it. When you open your thing, you look for where you put that in your file, in your folder. Which folder do you put it? Another way of doing it, you can even go to that folder and double click. Once you double click on it, even without opening it will open SPSS for you.
SPSS, okay.
And even without opening SPSS before, if you go to that folder, you double click and open for you. Because it's the things next. If you're having problem looking for it, you can share that your folder. If you share the folder, you open to that folder. If without opening SPSS and double click, you open. Or you cannot see it if you find it. Dr. Lagwe can share back. Let her share back what she has. I will just run it maybe tomorrow. Dr. Lagwe. Dr. Lagwe, you can share your own again.
Oh, I'm looking for the shares. Okay, I've seen it.
Okay. It's the same thing, it's the same one it's the same one we use. Did you close it that time? You know what? What he's doing, the thing is, he push it to one side. You'll have just click on that button. Share again. He push it to one side. That's what you just did because you open 2 times. Just share it. I will tell you what to do. Just click on that.
It has completely closed it, so I'm going to open it again.
Okay. Because
I think I found mine. Let me check.
Okay. Let Dr. Boju if he has found. Yeah. Okay, that's great. So without wasting time, go to the analyze. We want to look at sex and educational status now. Because educational status. No, wait. No, I don't want that one. No. Let's look at educational status and employment status. Yes, educational. Okay, go, continue now. Cross tab. Go to cross tab. Go to cross tab.
Okay, I'm already there. Can you see my? I'm already there.
And people can see it now. Then no. Educational status is the hardcore, is the exposure, yes. Is the exposure, yes. The role. Then employment status is the outcome. You can go and do all those things you did the other time. Go to exact. Click on exact. Or any of the statistics, anyone first. Exact. Click on exact. Because in case you need Fisher exact, click continue.
I think I'm continuing.
Then click on statistics. I think everybody is following. Because I'll share the video with you. You go back and click here, chi-square, continue.
Okay.
Yes. Go to sales. No, okay. Go to sales.
Sales, sorry.
Okay, no problem. Don't worry. Just share the result with us. What I want to show is on. Share the result with us.
Okay.
Because in the set, that's where you click the expected and the row something. Share the result with us.
Okay.
Dr. Henshaw, were you able to? Can you see where your data? You know where your data are, where you study. Were you able to study data somewhere? No, share again. No, second share. Go to second share and now double click. You have to go to second share. You through the Zoom. Second share.
Okay.
Share again, like you go to that share again, and now when you click on it, you now double click on the result view. Dr. Henshaw. Okay, no problem.
Hello.
Have you have where your data? You put your data. Okay.
Yes, but I said the files were still empty when I clicked on it.
How cannot be? It cannot be empty because it's the same thing I sent to people. Maybe let Dr. Olagoye explain to you. Maybe you understand you understand our language more than me. Because it's the same thing. Maybe it's something. You know what really happens that you cannot open it like you are opening Word document. You get the picture now. Though if you double click on it, it's supposed to open it. What's happening now? We are not seeing anything. Okay, scroll down. Scroll down. Scroll down. What's happening? You have done something. Maybe you have been using the data set before. You have done employment. No, it's education trans. Maybe you have done some analysis before, right?
I was following the other one, the one we were doing before.
And scroll down. This last one should be the last one. And if your RAM is very small, scroll down.
That's the last
one. That's it. Education and employment. Where is the chi-square? Okay, it's there. Yeah. Hello. What I want us to see is only that the arrangement is different. But look, what I want us to see is that you will see that there's person chi-square likelihood ratio. Feature is that you cannot see yet corrected chi-square. The reason is very simple. You know, yet corrected is only for 2 by 2. This one is 8 cell. This is 4 by 8. You get it now. This is for the degree of freedom here is 3 because 4 row minus 1, that's 3. 2 column minus 1. 3 times 1, 3. So there are 4 cells here, and the degree of freedom is 3. So it's only for 2 by 2 table, which the degree of freedom is 1, that you use yet corrected chi-square for. The only thing I wanted to say, look at this after the result. Dr. Odurishi, when we were talking about how do you know expected value, look at, even without you clicking on expected value, it will alert you. He said, look at what he says, is 0 cells, is 0%, have expected count less than 5. The minimum expected count is 5.75. You know, there are 2 conditions you are looking at here. You want to be sure that there's no one cell that has expected count less than 1. I want to be sure that nobody have expected count less than 5 in more than 20% of the cell. So that is why the 2 statement capture the 2. It will tell you that certain number of the cell that have expected count less than 5, there's none. That's why it says 0 is 0%. If let's say it's 1 now, it will tell you 12.5% because 1 cell out of 8 is 12.5%. If there are 2, it will say 2, 25%, because 2 is 25%. 2 out of 8 is 25%. So if there's any 1 at all that have expected count less than 1, you will know from the minimum expected count. Can you see? The minimum expected count is this. From the minimum, you will know if there's one that is less than 1 or not. By giving you the first statement, you know the proportion that have expected count less than 5. Can you see? So even the people that develop this software, they have good statisticians to advise them. They have programmed those things. Yeah. So without even you clicking on expected count, you will know. So, and by the time you know, you may decide to check which of them. You need to check. Don't just assume that it's the cell that has the smallest observed count. It may not work like that. How you know is that you look at the total, where the row total or column total is the smallest. So you will see, like this one now, if at all, you'll be surprised that if let's say there's going to be 1 cell that has expected count less than 1, it will be this one that has 10. It may not be this one that has 5. The reason is that this one, the row total is 15. The expected total and the column total is 115. Compared with this 5, the row total is 15, expected count 185. Can you see now? Can you see? So the expected count in this cell that has 5 is more than the one that has. So that is why you don't use the absolute, the observed value. You have to check the expected count. I think that is all. I don't know if there's any question on what we have done.
Okay, please, could you explain how to download the files? Because I had the same issue. It didn't open up.
How do you know that it's the same issue? Okay, you can share, Dr. Bojo, you can share. Dr. Henshaw, she has downloaded according to her. He says it's not opening.
The same with me now. It's just showing some characters.
Which file are you talking of?
The file we're analyzing.
Okay, all this file. I don't know where it's showing. No, I show you. I send it to you. Say you have seen it the other time now. I resend. Okay, share with us now. Share what is showing. You know what? Whatever is showing, you will share with us now. Let me see it. It's even good.
Okay, let me get.
Whatever is showing. If it has opened, just click on share and double click. When you see it, you will see all of them. You now double click on it. I'll be able to see. We'll be able to see. Maybe other people that are having the same problem.
I have a question, sir.
Okay, go on, sir.
Yes. So in that instance, so why do we prefer Pearson's? Why do we not take the likelihood ratio? How do we take the decision?
There's no. It's just that the Pearson is popular. There is, if you look at it, there's no even difference between one can use likelihood ratio, but you know, as examiner now, if you know people, whatever is common, is common. People are used to what is common. That's just it, and they can easily calculate it with hand also. Expected, you know, you don't need to go to logarithm. You know, when something involves logarithm. But now that you even use computer to do it, so just like what you said, sir, anyone can go, but it depends on the taste.
All right, thank you, sir.
Welcome, sir.
Thank you, sir.
Yes, sir. So I think Dr. Andrew, you want to share with us what you have. Share with us. Let's see the problem you're having with that later.
This is what I saw.
Yeah, how possible it is, but it's the same thing I sent to other people. ABO, it must be somehow your maybe your you maybe you want, you know, you try to open it with something now. Okay, you know what? How did you open it? Is it through SPSS you try to open it, or you just wanted to open it?
It didn't give me that option. Okay, this is my mail, so I downloaded it.
Okay,
and then tried
you know what you're going to do now. You know where it is. You know where it is in your distance. You know where.
I can find it.
You can find it. Okay. Now, close this one now. What you do is that click outside the Zoom. Click on your SPSS first. When it opens the window, then share with us. I will tell you what to do. Because if you want to, it's a program. If you want to just open it, it may not open unless if something corrupted the file. Let's just look at it.
So,
have you clicked on SPSS? I see open, just to open SPSS. You don't go and look for any file. Then share now. Share again. Double share. Then share again. Share that one with us. Click on share on the Zoom, through the Zoom. Share and double click on it. Because I want everybody to look at it, because many people may be having the same problem. Okay, now go to file. Go to file in this SPSS. Click on file on the left side. Open. Click on open. Open data. Click on data. Data. So look for it where it is. Okay. Is it that you save this in many times? Don't worry, just click on one of them. Click on one of them. Let me see. Double click. Okay, open. Don't worry, just open. Stop sharing. It stopped sharing, right? Hello? Because share with us again, because it stopped sharing. So what is it showing there with you? Hello?
Share it now.
It's not, you know.
Andrew, share it.
Okay.
The thing is slow. If your RAM is very small, it may be slow. Because you try to open the something now. But it's coming up.
Okay.
So it's not opening. But what is it showing you there? Because we can't see. But
you can't see anything.
It's coming. It's like we can't see everything. But just what is it showing you? It's showing you the data set, right?
I can't. Yes,
look at it now. You see, look at it. You know, the issue there is that sometimes your computer may show, it may not show it the same way it shows my own. But you have to, if you try to, it's a SPSS file. You cannot open it outside SPSS. So I don't know why I said that, but in my own, even if I don't even open SPSS, I go to where the folder, double click on it. It will open it, automatically open the SPSS and open that thing for me. I don't know, Dr. Henshaw, is this the same thing problem you have been having? Dr. Henshaw? Dr. Henshaw?
Yes.
Is it the same problem you have been having?
Yes, my own didn't even download that way. It was even showing like empty file. The file just looks empty.
You cannot. That we are saying the same thing. Sometimes, you know, when I send a trail of mail to people, they say they didn't see. If it's a trail of mail, you have to click on the first person they send the mail to. You click on it, you see the attachment there. You won't see the attachment with you because it's a trail. There's no, if I send something to you now, I need to send the same thing. There's no point attaching all the time. I will just forward the mail to you. Say the same thing I'm sending to you. So once somebody register, I want to forward the same thing. So when you are looking for you see somebody send you a trail of mail, you go and click at the first mail you send to somebody. That's where the attachment will be. So I don't know, like your own now. If you have it, and if it is, I think it's Gmail. If it's Yahoo Mail, you may be having problem downloading. That's Yahoo Mail. Gmail.
Yes.
Okay. Where is your this thing? Share your this thing with us. Okay, Dr. Dirishi, out. Share your this thing with us. Your folder, where it is. Go to that folder. Before open that folder where it is, and now share with us. Well, share the folder with us. I think some other people are learning from this because those are the problems of people we have. They say it's not opening.
I hope you send mine once we are done with the class.
I will do that.
Okay. Thank
you. Is it Gmail that you sent to me? Do you have Gmail?
No, it's Yahoo Mail.
You have Gmail?
I have to. The one I use more of is Yahoo. I don't think my Gmail is functional. I'll try and see if I can.
And because sometimes all these things to send all these things, they will not even Yahoo Mail is having problem these days now. Even today to open something Yahoo problem. So most of these things will not download. Gmail is and Gmail doesn't take time to. You can even create Gmail. Sign up and send to me. You sign up, either maybe the other one, no, just sign one up, new one, and send to me.
All right, okay, I'll do that.
Okay, Dr. Henshaw. Dr. Henshaw. Are we there?
Yeah.
So share that folder where all these things are. Share with us. Share just click on that share screen.
It will be difficult because I'm using tablets for the Zoom this thing, and I'm not using my computer for it.
Okay, if you are using at least you learn this one from this thing. So I don't know. Okay, but you are able. Didn't you install you have the SPSS now on your computer now?
Yes, I do.
And that's the essence of using. I said everybody should use connect with your computer. Connect with your computer. That's how what will make you to participate very well. So it's really like all this, apart from the theoretical aspect and the practical, I want to be telling you what to do. That is how you can learn it. So I think we can close for tonight. I don't know if there's any question on what we have done. Any question? Any question? Have we learned anything?
Yes.
Yes.
New?
Yes.
Yeah. So if there's no question, those are all those things that are very clear. Dr. Afefi, Dr. Kayode, if you want to answer me, you have to unmute yourself because I won't hear you. If you talk, I won't hear you. Okay, I think we can close. So what I will
Thank you, sir.
Yeah, welcome. I will make the recording to you. And that one also, if you don't have Gmail, you are just Yahoo Mail will not work. It will not even download it. So I think everybody has Gmail. I will just send the recording to you if you want to go back. And that is why, at least from tonight till evening tomorrow, you have the time to go through, to go to what we have done. And even the one we have done, just to run it. So with your laptop, with your SPSS, so let's see. And if you now go through it, if you should have questions, if you actually go through what we have done, go through the recording, the video, and you have questions. If you don't have questions, it may be that you understand everything or you didn't go through. Okay. I think everybody, good night.
Thank you. Good night.
Good night. Thank you. You're welcome.
Thank you.
Okay. Thank you.
Thank you. Good
Thank
night.
you, sir. Good night.
Good night.
Good night, sir.
Good night, sir.
Good night, sir. I've sent my Gmail.
Okay. Okay.
Distance.
You're welcome.
Good night, sir.
Good night. Good night. Yeah.